Good morning, everybody. Thank you so much for being here today at the workshop on quantum computing and sensing for weather and climate application. We are very excited. We worked for 1 year on this, so we are very excited to have this workshop. For people that don't know, CLIVAR is the Climate Variability Predictability Program. And the focus is understanding the dynamics, the interaction of what's going on in the climate and in the weather. So before we start with the session, I would like to mention who is organizing this. So it would be myself, Ruben, which will continue. I will start this presentation. Ruben will continue. Marlu and Anish, these are the local people from Boulder. Then Swamit from University of Wisconsin, Felix from University of Oxford, and Carl from University of Sherbrooke. So we would like to thank all these people that put this event together. And this could not be possible without the help with Alyssa, which is sitting right there. Thank you, Alyssa, in advance, and we'll thank you at the end. And Mike and Jessica, whom you met when you entered. Let me take a couple of seconds to thank the sponsor. This event will not be possible without the sponsorship of the Office of Naval Research. They believed in research in quantum, in sensing, computing, weather, and climate. So we really would like to thank them. And again, please join me in thanking them. So this is an event that brings together two different communities, the quantum community, the weather, the climate, and you must see this as the following of other similar events. In 2023, GE Vernova Advanced Research in New York, where I work, we organized a workshop sponsored by NSF on quantum for climate and sustainability. We had like a 2 days breakout session, talks, a lot of panels, a lot of discussions. At the end, there is a report which is available on the website of this event. The year after, in France, in Paris, there was another event, Quantum for Climate. Again, the idea was to bring together different community. And 2 months ago, at Stony Brook, there was another workshop, still sponsored by NSF, and it was quantum information science. And you will have an overview of this by one of the first speakers, Jason Hyon. And the goal is similar in all these workshops and even today, identify what are the near-term application that could benefit for quantum, from quantum, and establish a community, bringing together different community that they will not talk naturally, and we think that this would be the power to actually push this field. So if we think about quantum for climate and weather, we think about problems that are really complex, that traditional computer have some difficulties to solve. So we think about computational complexity, models that require high resolution, nonlinear equation, where a small change in the input can explode as the output. So can quantum computing do better than that? And then data assimilation, we have so many ways to get information from the environment. But do we have way to combine this information in a good way? That's a challenge. Again, we hope that quantum could help solving that problem. And when we talk about sensing and use for forecasting or for situational awareness, what about if we have better sensor and if we have more better resolution in what we can actually detect, the changes that we can detect? And then the subgrid processing, some of the problems are so like small scale event that we cannot model them, so we estimate them. Can we do something better? Not estimate, but really model the real event. So this is an overview of some of the applications. There are more, but something that we think quantum could help. And we hope this community brought together, we could have discussions and we could have an impact on the decision, what's the near-term research. I think this one would go to Ruben.
Thank you, Anna Rita, for providing the context for this meeting. So I'll start with some objectives, what we're hoping to accomplish. We want to, first of all, showcase what quantum technologies can achieve today, and we'll do that with presentations and posters. But we also want to increase collaboration between quantum, weather, climate scientists, and mathematicians to develop new research projects. And we'd like to predict how quantum technologies will be used for weather and climate applications in the coming years as the technology and hardware matures. So the kind of concrete goal of this meeting is to publish a meeting summary in a journal that could be in something like BAMS for a broad audience if you're familiar with that journal. And we'd like to do it by the end of 2026 this year. And that will include major workshop themes. It will include new developments within the various fields, list near-term applications, and key discussions that were had during this meeting. It will also have, hopefully, a consensus and differing views that were reached during some of our discussions, and some recommendations that were made as a result of this meeting. So now I'll just give an overview of the agenda. Today, we'll start with quantum sensing for weather and climate applications, including a panel discussion. And then the second session will be quantum computing for Earth system models. We'll then have a breakout session for both of those topics. And then we'll conclude today with a networking event at the end of the day. And then tomorrow on Tuesday, we'll start with quantum algorithms for differential equations. The second session will be quantum algorithms for optimization. And then we'll have virtual and in-person poster sessions as well. And then we'll also have a breakout session, which will be on both of those topics, so algorithms for differential equations and optimization. And then finally on Wednesday, we'll have a session on quantum computing for extreme weather events. And then we'll have a breakout session on that topic and also special topics, including like workforce development and things like that. And finally, we'll conclude that day with a tour of Elevate Quantum, which will start at 3 o'clock, and transportation will be provided if you need it. So I'm really excited for that tour. So what's our workshop philosophy? Well, we've brought together researchers spanning a wide range of topics, career stages and backgrounds, and participants are joining in person and virtually. And we really do want every voice to be heard so that we can capture the full range of perspectives. We really encourage everyone to participate. This is more than just people giving talks and presentations. It's also discussions so that everyone can share their perspectives. So ask questions. Thoughtful questions are essential for learning and documenting for our meeting overviews. Please take the time to engage with poster sessions, both in person and virtual, which are a great opportunity for networking. I personally really love posters because you get one-on-one discussions with the authors. Okay, some important notes. So in-person participants, please speak into the microphone so that you give those online the ability to hear you. And please share your name before giving your comments or your questions. And virtual participants, please use the raise your hand feature when asking questions. And when you're called on, you can unmute and turn your camera on to share your questions or your comments. For posters, in person and virtual, those can all be viewed online in the poster gallery, and the in-person posters will be upstairs. And then my last slide here is just on some general information. So if you're looking for Wi-Fi, it's a UCAR visitor. There's no password there. We'll have a group photo today at 10 a.m. during our first break. There's elevator access on all floors, and bathrooms are located across the lobby in the back left corner. And we have breakfast and lunch provided all 3 days of the workshop. If you're interested in connecting, you can find CLIVAR or at US CLIVAR on Blue Sky and LinkedIn. And then finally, just some very helpful folks, Jessica and Alyssa, who you can ask some questions, as well as anyone on the organizing committee. So before we get into our next session, we first would like to give an overview of a recent workshop that took place, which was the NSF Quantum Geosciences workshop. I unfortunately couldn't attend, but I'm excited to hear the overview. And to give this overview, I'd like to welcome Jason Hyon onto the stage, who is the Chief Technologist for Earth System and Technology at JPL. So yeah, Jason, please come up.
Good morning. I'm Jason Hyon. As introduced, I'm the director of Quantum Space Innovation Center at JPL. Before I get into the quantum sensing talk, I'd like to give you a short, brief summary from the workshop recently held at Stony Brook University, sponsored by NSF. This was mainly focusing on geosciences. So I think the themes of the approach and the outcome of this particular workshop is similar, but we're tackling on geosciences rather than climate and weather. So those are the kind of two main differences. But you will see a lot of similarity as far as what the outcomes are, what the surveys, and what the discussion points were. So we had about 120 people from various organizations. So as I said, the experts from academia, national labs, industry, NASA, NSF, DOE, NOAA, and other federal agencies. We looked at how quantum information science can address major geoscience challenges. We focus mainly on two areas, quantum computing and quantum sensing, just like the theme. Seems like every week there is a workshop of some sort somewhere in the United States talking about the exact same thing in terms of how quantum technology or capability can support what their needs are, whether it's a science or financial or biomedical or whatever. But the key message from the workshop was quantum technology should augment, not replace, classical computing and observation systems, becoming specialized capability within hybrid science workflows. So I think it's critical to identify where the classical sensing and computing is important and it has an advantage, and then try to identify where the gaps are and then how quantum can fill that specific gap rather than try to say how quantum can do everything for what you're doing today. There are three main areas. Like I said, quantum computing, we discussed voice system modeling, uncertainty quantification, optimization, data assimilation, inverse program, partial differential equation solvers, and so forth. So those are the kind of potential areas of how quantum computing can advance or help. As far as the quantum sensing is concerned, quantum gravity radiometer, atmospheric trace gas sensing, quantum lidars and radar, those are like really far-term concepts. Atomic clocks, magnetometer, and entangled observations. So those are the key discussion points. As far as the near-term opportunity is concerned, participants agree that quantum sensing is going to be closer to operational deployment than quantum computing. And I will give you more details about what quantum sensing capabilities are currently existing in the next talk. As far as the strategic findings concerned, hybrid quantum classical systems concerned, quantum processors integrated with the high-performance computing, quantum sensors integrated with the existing observation systems. As far as developing or establishing a community benchmark to evaluate in terms of scientific benefits, accuracies, uncertainty quantifications, and cost performance in terms of utilizing quantum over classical systems. So we need to have a community-based metric in a way that we can evaluate and see how respective system can advance or benefit. Validation infrastructure needed for test beds, field demonstrations, calibration standards, side-by-side comparison with the classical instruments. So those are kind of activities that we would like NSF to consider investing in establishing. And then strong collaborations needed. As you heard, many of the agencies, many of the researchers, universities are doing very similar things. And I think because resources are very limited, it's better for each specific agencies and organization to take responsibility of a specific area and advancing those capabilities, and then try to figure out how all these different development can integrate together so that we have a fully vertically integrated infrastructure in a way that people can benefit from each other and they understand what their research is going to be infused or who are they going to collaborate with. As far as the workforce and infrastructure priorities concerned, we recommended short courses, summer schools, graduate fellowships, quantum playgrounds, cloud-based quantum computing capabilities, and industry internships. So try to have agency-wide opportunities for students to have access to these different opportunities so that we can grow our quantum workforce. And through different short courses, people can benefit through. And we noticed that probably 80% of the current graduates in the quantum world are all going to quantum computing because that's where the money is, so to speak. But we like to also attract these quantum physicists in the developing quantum physics, quantum sensing areas, quantum networking and communication areas. So this is a way to entice these students into this field. As far as our infrastructure priority is concerned, near term, we want to, like I said, build benchmark data sets, tutorials, and pilot projects. From the midterm, we're 5 to 10 years, hybrid high performance computing and quantum computing environments, sensor test beds and validation campaigns. As far as the long term, we want to build national centers, distributed sensing networks, fault-tolerant quantum computing and communication infrastructures. So that's the kind of outlook for the nation, not for specific individual agencies or specific individual universities and research organizations. So as far as the recommendation and path forward is concerned, we want to build a NSF to consider open competitive programs with a quantum computer scientist and then actual climate or the geoscientists working together and come up with the quantum algorithm addressing geoscience challenges, quantum sensor developments, cross-disciplinary collaboration opportunities. From the program agency itself, we want to establish shared national infrastructure, providing access to quantum computers in the cloud environment, benchmark repositories, validation facilities, and shared test beds. And then, as I said earlier, build a coordinated national ecosystem to integrate all these investments and research breakthroughs. And overall conclusion is, it represents a long-term strategy. It's not a short-term. We're looking, for fully, integrating quantum computing capability and sensing capabilities. We're looking at 10 to 15 years down the road. But there are a lot of activities currently going on. So we should have an outlook of a long-term vision. And then we also need to have a vertically integrated kind of architecture in a way that where do you fit, what your research is accelerating in, and how you're going to interface with. Try to understand those interfaces is critical at this point. And then, provide a sustained investment in benchmarking, workforce development, shared infrastructure, interdisciplinary collaboration, also with the other government agencies. So those are, I think, the key outcome from the report. NSF is going to use these recommendations to develop future opportunities and programs based on those. So hopefully from this workshop, I really want you guys all think about where you fit, what your research is, how you're going to integrate with the existing other programs. So, try to ask those questions will be very helpful. Any questions before I get into the next topic?
I'm Rubayat. I'm from NCAR here. So we work with NWP systems, so numerical water prediction systems. So my question would be from the colleagues who are currently working on quantum computing and algorithm development, how can we help? What sort of tools or software or modeling contributions that you guys will be needing from weather or climate modeling communities?
Yeah, I think, we asked, quantum computing industry is what is the killer app today that you think that clearly demonstrate quantum computing has a supremacy over high performance computing? Nobody could answer it today. We really don't know what the impact is. I think there is in the quantum chemistry, people, using quantum simulators to estimate the total energy when you have a different chemical reactions. Definitely there is a benefit of optimization and so forth. But other than that, we're not clear in terms of what the quantum computing is gonna, algorithms gonna be provide in a way that outperforms the classical or the traditional high performance computing algorithms. So I think the critical thing is if you can think about what is that one killer app that will really carry the day, really selling it, why quantum computing is important. Until we have that killer app, I think the quantum computing industry is, mainly focusing on financials, biology and medicine type of research activities rather than physical sciences, geosciences, and climate sciences. So I think the key is, I beg you, the whole community here, to try to think about what is that killer app.
question on whether there was a consensus regarding quantum sensing being more mature or might have more near-term applications for climate and weather versus quantum computing.
Yeah, I mean, definitely, I'll go through some of the quantum sensing advancements at this point at NASA, but there are a lot of investments in developing quantum sensing capabilities today. Gravity radiometers, magnetometers, Rydberg microwave sensors, and so forth. Those are currently flying in the high altitude balloons and aircrafts. We're going to be flying these quantum gravity radiometers in 5 years from now. So there are a lot of developments. And the key is the high power lasers, the photonics developments. They're all kind of coming together because of the benefit of developing quantum computers. Just like the old days when the semiconductor foundry were developed, established to build a high performance computers. Quantum sensing, the classical sensing community took a benefit of these semiconductor technologies. And I think we see the same trend where quantum computing industries are investing heavily on developing these component technologies, and we're utilizing these component technology in building sensors.
And is this report and workshop material available online?
Right now it's in draft. NSF's going to finalize it, and as soon as it become a final version, then we'll share that with the workshop.
I'm Vivek from NCAR, work in remote sensing. You mentioned the report, you mentioned the quantum technologies augment the current thing.
Mm-hmm.
Shouldn't be replacing the classical thing. I'm not sure what is that reasoning behind that, why it is.
So quantum computer is good at specific things like optimization, try to understand the overall trends. I'm not a quantum computing expert, so I can't say, but we have Alex here from JPL also. So it doesn't do everything better than traditional high performance computers like 1 + 1, 1 × 1. Those type of algorithmic computing are far superior using high performance computers. So you just need to understand like how you want to optimize your overall computation using both capabilities.
Yeah, I'm more referring to quantum sensing, not the computing.
Oh, I'm sorry.
Yeah.
So I'll talk about that in more detail. So why don't
Okay.
you hold off, and then I'll go through the quantum
Okay.
quantum sensing, why it's better in some areas, and I'll try to focus on those.
Okay, thanks.
And I asked a director for Amazon Web Services. He's developing quantum computers for the Amazon. And today, if you were to build a quantum computing facility, what would it look like? So you see a data warehouse, and 95% of that data warehouse will be filled with a high performance computer. And then only 5% will be quantum computer, because you need to do error corrections, you need to control the quantum computer. So the 95% of the footprint is going to be purely high performance computer in controlling the quantum computer. So you see the perspective.
In this workshop, we will bring together the quantum and the climate and weather communities. And one part of quantum that will be very important to highlight here is quantum sensing, where we try and explore to expand the measurement capabilities beyond the classical limits. And we will seek the measurement gaps in climate and weather, where these capabilities could come in especially handy. In quantum computing, you see claims of quantum advantage from time to time, which then gets heavily debated. Also currently, there was just a claim last week. I can't comment on that. I'm more on the quantum sensing side, but I can comment on quantum sensing, where we actually span a range of technology readiness levels. Some are just still in the lab, but others are out here, right now, giving a quantum advantage. So we'll hear more about all those quantum sensing modalities today. In the quantum sensing session today, we will start with 3 presentations before the break. After the break, we will continue with a panel, including an open discussion where you can share your questions, your input. And then this afternoon, we will have a breakout session to bring these discussions even closer. I really look forward to the presentation of our first speaker, whom you have seen already, Jason Hyon from NASA JPL. Jason is the director of the Quantum Space Center at the NASA Jet Propulsion Laboratory. He's also the chief technologist for the Earth Science and Technology Directorate there. And at NASA, he advances cutting-edge technologies for the NASA Earth Science mission, including using quantum sensors. Jason, please take it away.
Thank you. So before I get into quantum sensing in detail, try to give you some quantum 101. How many people are not familiar with what quantum sensing is? So a lot of you, so it's good. So let me go through some of these rationale behind using quantum sensors. So quantum physics is a science of small objects such as atoms, molecules, and subatomic particles. The ability to isolate, manipulate, and design a quantum system using these quantum phenomena in the real engineering is the key in developing quantum sensors. The critical thing is the invention, and availability of high power, high stability laser was the key. And those lasers, once again, were being developed through quantum computing industries, and we're greatly taking advantage of these laser techniques. And then we're using these lasers for trapping of single atoms, cooling them down. Cooling them down means the atoms are very stable, it's not moving. So if you know in the atomic state, a lot of these atoms and electrons are moving, and you can't do the measurement with these moving atoms. So you need to cool and really stabilize that atom, and you use lasers to do that. So we call it laser cooling. It's not like a freezer type of thing. You're actually not stabilizing the atoms too, so that it doesn't move. Quantum physics exhibit non-classical behaviors such as a wave-like interference, superposition of individual systems, probabilistic nature of the measurement, and entanglement. So we're using these type of different quantum phenomena in applying those techniques in developing these quantum sensors. The objects are cooled down to these quantum effects, and then slowing the atoms in the quantum state, we can engineer a system that exhibits quantum dominated effects. Okay, and we'll tell you what those are in the later charts. So what is a quantum sensor? A sensor take advantage of, like I said, these different quantum phenomena to build these sensors for acceleration measurements, rotation measurements, magnetometer measurements, gravity measurement with extraordinary precisions. The quantum sensors are inherently stable, depends on the fundamental behavior of the atom, and unlike the classical sensors where it requires a constant calibration, sensors are based on atoms, are also orders of magnitude smaller because you're manipulating individual atoms rather than electromagnetic waves. And classical because the millimeter-sized atom clouds can effectively build by billions of these atom clouds. So individual atom could be individual sensors. So you could give you a lot better precision measurements. And then sensor holds a great promise for space-based applications such as the gravity sensing, like I said, microwave sensing, navigation, and timekeeping. And I'll give you some of the examples of what's been going on. So why space? Why NASA, JPL is doing this? Space can provide a intercontinental quantum communication that's not possible with the fiber optics. So if you were to connecting multiple quantum computers using a fiber, there's a lot of noise introduced. So you cannot just have a free space entangled quantum computers. So utilizing free space optical links to do these networking is critical. Quantum space environment also, the space environment also provides a quantum metrology that can perform far greater precision than terrestrial settings. And then space provides a long baseline network of far distributed quantum sensors. So if you wanted to entangle multiple telescopes to observe exoplanets and other phenomena, utilizing these entangled network of telescope will greatly advance or enhance the resolution of these telescopes. So that's the reason why NASA is getting into space, utilizing quantum technology. So a little deeper, here are the kind of different types of quantum sensors. The bottom left is the classical methods using microwave signals to do current detections, radars, radiometers, spectrometers, and ranging using satellites are the current techniques. If you're manipulating atoms and photons, you could build something like the atom gravity gradiometers. You could build accelerometers and gyroscopes. That's one you see on the bottom left. in a both on the terrestrial and space environment. Top right is quantum algorithms. So using quantum optics and quantum behaviors, you could do a very long baseline BLBI type of measurements, ghost imaging, photon counting LiDARs, and then space communications. So those are the kind of techniques and technologies currently being developed, both by government agencies and industries and universities. And there is a perceived competition, international competition. So Europeans are heavily involved in investing and advancing these technologies. So does the United States and then Asian countries. So we're kind of in neck to neck, so to speak, in terms of the current state of the art is concerned. But who's going to have the breakthroughs in terms of having a quantum dominance in near future? We see, I can see at least 2 to 3 years you'll have an operational capabilities in this area. And then lastly, if you combine all these different quantum phenomena, that will be the quantum computer. That's why you'll see that the sensors are more mature, algorithms are more mature than the quantum computer, because you need to mature all these techniques first in order to have a fully functional quantum computer in the future. Okay, so that's why the timeline of sensing and then computing eventually. So in terms of building the standard quantum limits concern for the different measurements, we use techniques like a squeezing. So you have amplitude and phase. LIGO is the way to detect gravitational potentials. It's in the ground network. We are squeezing a phase to get the amplitude information. We're using interference, using atom gravity gradiometer. So basically you're freezing a two cloud of atoms, and then you apply different polarized laser lights. And then as you go through different mass over it, these will pull the clouds up and down, so to speak, as you go through different mass. And that's how you interpret the gravity gradient using the interference patterns. Entanglement, your Heisenberg limit says if you have n number of sensors, you only get a square root of n effects. By using entangling methods, you could get the true n number of sensors. So by entangling these quantum sensors or quantum ground network, you get the full effects of n number of sensors. As far as the metric for quantum advantage is concerned, determine how much information could be stored in a single photon for quantum computing, and then truly, kind of measure the gravitational potentials and gravitational force. You could detect the dark energy also. So there are different techniques people are thinking of using these different quantum sensors for different disciplines. Quantum sensors use the quantum mechanical properties of light and matter to improve sensing capabilities. So that's the kind of bottom line of developing these sensors behind it. So what we did at JPL about, 6 years ago. So we looked at all the science challenges, that the column on the right, and then we looked at all the different quantum sensing techniques that's available and try to map what techniques are relevant for solving which science. And then we try to identify whether the capability exists commercially, exists in lab, or exists only in the theory. So try to assess the maturity of the techniques and technologies. So build something like this could be very useful, and you understand where kind of you need to emphasize and invest in technologies and supporting particular science challenges and needs. So we looked at both the planetary science, astrophysics, earth science, telecom, and then also national security applications. And the key bottom line on the science areas in the earth science, by using quantum gravity gradiometer, we could do a mass change in terms of large ocean circulation, Arctic ice melting, groundwater movements, and so forth. So those are the critical things. So GRACE missions, right? It's a twin satellites using microwave or optical ranging between the two satellites. As you move over different mass, it's going to either push or pull these two satellites. And by measuring those differences, you could detect the mass change underneath. And it is relying on GPS signals because you need to have a precision ranging between the two satellites. However, if you're to fly these GRACE-like missions in other planetary bodies, the moon or Mars or ocean giants or ice world, there's no GPS signals to range these two satellites. So having a quantum gravity radiometer, it's a single spacecraft with a two cloud of atoms and an interferometer. You can measure the exact same thing, and it doesn't rely on GPS. So that's the great advantage of having a quantum gravity radiometer over a traditional GPS relying ranging two satellites. As far as astrophysics is concerned, if you fly these gravity radiometer in a tetrahedron configuration, then you can completely kind of zero out the gravitational force. So whatever the force that you detect out of the gravitational force is the dark energy or dark matter, right? That's how they are thinking about developing a mission concept that's relying on gravity radiometer. For planetary gravity measurements concerned, if you want to do resource utilization, you need to find where the water is on the moon. You need to find where the caves, underground caves are for the habitable environment. You need to measure the seismology and gravity gradients. And, like I said, because they don't have a GPS signals, you need to rely on something like quantum gravity radiometer for utilizing that technique. And not only we're kind of proposing how this could be helping, but we also try to come up with a metric, real metric. So using a QGG, quantum gravity radiometer, you get 3 times better accuracy than the current GRACE baseline. Astrophysics, the dark energy model, we could improve by 50 sigma in 1 year. And then, like I said, the planetary science, you could detect these gravitational, the mass changes underground or underwater using this technique. I'm going to talk a little bit about the investments in workforce for quantum. Here is the history of different initiative by the United States government. There's a China, competition also. In terms of Black Swan events concerned, if China were to develop or demonstrate a particular capability, what is our response is going to be? How are we going to catch up quickly to come up with this Sputnik type of event? And then the White House also came out with the National Strategic Overview of the Quantum Information Science. The Congress passed the National Quantum Initiative Act in 2018. It expired in 2025. And then there is a new reauthorization bill that's currently on the floor. We don't think, because of all these changes in the congressional staffing at this point, we don't think it's going to be reauthorized until 2027, but there is a strong push in government investment in the quantum areas. There is, like I said, there's a lot of investments going on, but the problem is it's not coordinated, it's not vertically integrated, so that there is a lot of people doing similar things, not doing something that kind of eventually be built as a fully vertically integrated capability to demonstrate, and that's something that we need to address. And like I said, there is the new the bill that's currently being proposed as a reauthorization bill, and then there's a executive order just came out, and from the NSF and NASA, within I think 2 years, we need to come up with a 5-year tactical plan in terms of how we're going to advance the quantum computing and quantum sensing areas. So each respective organizations are working to build this roadmap, demonstrating capabilities and so forth. Here are the opportunities from various agencies because of the new bill, NQI bill, and the executive order. Different government agencies are investing heavily. And not only the government agencies, but you will see there's a lot of public investments, venture capitalists, individual industries. They're spending a lot of money in investing in this area. And obviously, most of this money is going into quantum computing. There are at least, I think, 15 different industry out there that's building quantum computers, whether it's a large scale like IBM's and Google's, kind of middle scale IonQs and Inflections, and there is a startup companies. So there are various stages of these quantum computers. We don't know which technique's going to survive. There are at least 3 different types of quantum computing technologies currently being considered. Just like the old days of VHF and beta tapes, we don't know who's going to win out. but maybe one particular approach will dominate at some point. But it remains to be seen at this point. Here are kind of state of the quantum industry. This was done by North Dakota Survey. And if you look at the pie chart, most of the the investments in the quantum software, quantum computing hardware, and then quantum communication areas. And then you see the light green part on the top. That's where the quantum sensing is. So like I said, truly the whole quantum industry is driven by quantum computers and quantum communications. And as a quantum sensing community is concerned, we're taking advantage. We need to monitor what's currently being invested and developed, and how we can take advantage of those capabilities in applying it to our quantum sensing technology. Okay, so it's clearly we want to rely on quantum computing industry to benefit our quantum sensing capabilities. And as you can see, United States has the most investments currently going on. But as you can see, China and the European countries and Asian countries are heavily investing in this area. So, like I say, it's a race at this point in terms of who is going to come out as a winner as far as the quantum computing is concerned. It's remained to be seen. So, getting to the main point in terms of quantum sensing and climate. At NASA, we rely on NASA Decadal Survey. Every 10 years, the community of scientists get together and try to prioritize what are the key measurements and observations are needed in addressing climate. And NASA has changed the discipline into 5 spheres: atmosphere, land, ocean, I think climate, and then hydrology. So those are the kind of 5 key spheres. And then within those spheres, they define what are the key critical high priority science questions are. And then in order to answer those science questions, they identify what the key observables and measurements are. And then along with that, also talk about the Earth system modeling and digital twin needs in terms of reducing the uncertainty quantifications concern. And then there's also emphasis on applications in terms of not just doing a science for the research, but actionable science in terms of how can we utilize the scientific knowledge gained to apply in applications, mitigating climate impacts, and then near-term and far-term impacts like the weather and climate. So those are the kind of key drivers that's going to drive the needs for the quantum sensing capabilities. As far as building a affordable mission is concerned, as you know, affordable science, we can't be building billion-dollar missions anymore. We have to be very cost-conscious, good enough measurements to still advance scientific knowledge. So I think the quantum is going to play an important role of doing that. But these are the key considerations that we have to think about. And then once again, assess how quantum sensing enhance or enable technology gaps, lowering the cost, like I said, using quantum gravity gradiometers, Rydberg microwave sensors, having a single radar receiver that could detect multiple signals at the same time, it will give you a tremendous help. So if you were to do a 3D mapping of a biosphere, you need at least 5 different radars. You need to have a Ka band, top of the tree, L band for the density of the tree, and then the soil moistures and deep root zone soil moistures, you need UHF and BHF. At least you need 4 different radars to detect the full 3D structures. Having a single Rydberg sensor that can tune to all the different frequency in real time, you just need a single receiver. So there's a tremendous benefit of using this type of technique. Improving sensitivity to reduce uncertainty quantifications using constellations, concurrent measurements, and 3D topography. Those are the kind of critical measurements that's currently missing. And as it was highlighted, you do a lot of estimation at this point. We want to do make these measurements so that we can reduce the uncertainties. And then enabling measurements where the classical sensor cannot do today. Entangling sensors, like I said, entangling multiple telescopes, entangling multiple gravity gradiometers in space, you get a lot higher resolution and benefit. So in a typical operation-informed Earth system modeling, You have these various satellites do critical measurements of the ocean and climate. You have the in situ models on the left using, and so this is the world of NOAA and NASA. That's the world of NSF, so to speak. And then there's a critical coupled ocean and sea ice general circulation models using physics, classical physics that we know. And we use all three measurements and technique to build this digital twin. And that scenario is not going to change. So the key is, how do we optimize? Do we still need to fly tens of these different observations still in order to continuously reduce the uncertainties of the Earth system model? In situ sensors also, so optimization, try to make this viable digital twin, but still utilizing less observables, rely more on models maybe, and those are the kind of critical thinking that we need. So, at JPL, we do, our main goal is to provide observations. So this is a greenhouse gas observation. So we have OCO2, OCO3, we have a solar-induced fluorescence measurements, and those individual measurements get assimilated into models. We have a process models, we have a system models, we have algorithms and data assimilation techniques. So all these different process models gets integrated as creating a digital twin. And then once we have this digital twin, then we could use that for forecasting and prediction, right? So we use that information to inform boundary organizations like FEMA, USGS, and so forth, and UN, and we provide these predictions where some of the organizations need to address application and climate impacts and so forth. I want to kind of drill down one level deeper. So in terms of mass change or the climate variability on the ocean science is concerned, the GRACE mission currently has three main objectives: climate variability and change, global hydrology cycle and world resource, and Earth surface and interior. So in the current decadal survey, they identify specific science questions in these three discipline areas. And as I said, in the measurements concern, we're using a GRACE missions to using satellite to satellite tracking, using twin satellites. And then through quantum gravity-gradiometer, we come up with a new measurement technique called the QGG, and we're advancing this technology today. And like I said, by year 2030, 4 years from now, we'll be flying the new gravity-gradiometer sensor to replace the GRACE mission. So that's the thought process in terms of, here is the key science question, here are the specific measurable that's going to answer these science questions, and then here are sensing techniques that's going to deliver that measurement accuracy. And then once we define those sensing technique, then we go on and develop that particular sensing capability. As far as the prioritizing the key science questions, here are the key measurables in addressing climate variability and hydrology cycle and Earth surface and interior. And then we prioritize which ones are highest priority, which one's the medium, and then which is the low priority. So, you cannot answer everything. You cannot do everything with one single sensor. So we try to work with the science community, try to figure out, what are the most high priority science that we need to answer, and then how do we deliver that measurement in the most optimum way. And once you have that science question prioritized, then here is the science objective. And then, you break it down into science requirements in order to answer these objectives. So, one of the critical things is you need to be able to detect mass change, 15 millimeter equivalent water heights over 300 square miles, 300 square kilometers. Okay, so that's the accuracy that we need in order to answer that science question. Then we come up with the measurement requirements, and then we try to come up with an instrument that's going to be able to answer that question. So the bottom line is, in order to detect that change, you need to have a 1 micro EDVASH. So single EDVASH is two people walking 2 meters apart and walking like this. And that's the force you feel. That's 1 atbash. So we're talking 10 to the minus 6 atbash measurement from space in order to give you that 15 millimeter equivalent water at 300 kilometers square. So that's what we're trying to achieve. And this kind of shows you, what is the current GRACE can do, which is the top, 3 questions that you can answer with the sensitivity that GRACE give you. And then with the quantum gravity gradiometer, it gives you 5 more additional science questions. It answers 5 more additional science questions. So there's a significant benefit of using a QGG over traditional satellite-to-satellite tracking methods. So we need to do a lot of these benchmarking, metrics, analysis, community-driven discussions in order to kind of take one approach over the other. So this is how the quantum gravity gradiometer look like. You have 2 chambers. You cool down the rubidium atom source. You generate millions of atoms. You use lasers to really cool down these cloud of atoms into 2 stable states. And then you apply 90-degree, 180-degree, and 170-degree polarized lasers. And then as you fly over different mass, it's going to generate a fringe patterns. And that's how you measure, the gravity gradient as you fly over different mass. And that's the technology. We're working with the inflection. We have worked with the IonQ, also Aerospace. So there are many different industries that's traditionally a quantum computing companies. We're taking those technique and technologies and building these systems. I'm not gonna, due to the interest of time, I have 3 minutes left. So I'm just gonna. These are the steps that we need to take to how you cool the atoms, transport the cloud of atoms, and then applying an interferometric technique. We're going to have the engineering model. We're going to take that over to Hanover, Germany. They have a Einstein elevator. You could get the 4 seconds of microgravity environment, and it operates 8 hours. So up and down consistently. And you can actually create a microgravity environment to test the payload. So we're going to have the engineering model finished by next July. We're going to be doing a lot of testing. And then the ultimate flight model is going to be delivered 2029, and then we'll fly in 2030. The Rydberg's radar that I told you about, basically, like I said, it uses a rubidium or cesium as a source, and you excite the atom into a rubidium energy level. And once you get into that Rydberg energy level, depending on what microwave signal that's incoming, whether it's a Ka band, L band, UHF, VHF, it uses a different energy level to stimulate that particular energy. And that's how you translate whether you're receiving on Ka band or L band or UHF band. And there are a lot of communication satellites out there, XM radios, UHF signals for Navy. So we use a lot of these different communication satellite signals. And then this is a receive only to detect those capabilities. As far as the JPL is concerned, why JPL is doing it? We're the only NASA centers building these quantum sensors and actually flown in space. Cold Atom Lab currently operating in international space stations. We also flew a deep space atomic clock. We also flew the micro ion clock. So this is the microwave clocks. So it depends on the different clocks. You want to be able to do time transfer, frequency transfer between the ground and space. This technique is needed. So we're the only ones actually built actual systems that's currently flying in space, and we're continuously advancing these technologies for the future. We have about 12 different test beds already. So if you are developing specific components that you want to see how the components work as a system, you can also work with us in integrating with our test beds to fully test out the system capabilities. We, not as a quantum space innovation center, we also have a quantum hub. So these are the universities that are members. And if you want to join our hub members, you're more than welcome. We provide monthly seminars, internship opportunities, and then we do matchmaking based on specific opportunities. If you're needing a particular capabilities or a particular technology, we do matchmaking for them, for you to capture opportunities. So that's the overall goal of hub members, and it's continuously growing. And this is how reach us.
Thank you, Jason Hyon, for a fantastic talk. Please keep your questions in mind or write them down. We will have a discussion in half an hour where you can ask all your questions to the 3 speakers. So a warm applause for Jason again. And now we continue the quantum sensing session with our second talk. Panda online already. Cristian, please, you can pull up your slides in the meantime. We're very excited to have Cristian Panda join us from the University of Arizona, where he holds a position as an assistant professor. He is an expert on quantum gravimeters, working on that now with his group, previously having done a postdoctoral scholarship position with Holger Müller at UC Berkeley, and prior to that, completing his PhD at Harvard University. Warm welcome, Cristian.
Great. Well, thanks for having me. It's really exciting to be here, be able to talk about our work. It's sort of continuing along the same introduction that Jason gave, so I was really happy to see that. It makes it a little bit easier for me to kind of keep up on the motivation. So what we do here is also a type of quantum sensor that is sort of aimed towards measuring gravity and measuring it really precisely. Sort of the differences, compared to Jason's sort of approaches, in which the atoms are falling on the Earth's gravitational field. Here we use an optical lattice to hold the atoms in place. So we've been super excited to develop this over the last few years at Berkeley and now at the University of Arizona for the last couple of years. And really the goals are to achieve this extremely long coherent spatial superposition state. So now we can measure these atoms, spatial superposition quantum coherence after up to 70 seconds. So just a little bit longer than 1 minute. And we are super excited to do a first measurement of gravity using this new method by measuring the gravitational field of this tungsten source mass that you can see on the right here. And the precision of that measurement was even better than what we've been able to achieve previously. So, I have a slide on motivation. I can go really quick because Jason already did, such a good job introducing this. There's sort of different ways to measure gravity. You can measure the strength of the gravitational field. So that's on the left, gravimetry, or you can measure the gradient in that field, gradiometry. The data on the left is data from this, extremely successful mission of GRACE and GOCHA. They're satellites that circle the Earth and measure its gravitational field. You can see that the data is shown in this sort of funny units, milli-Gauss. So it's from Galileo. It's basically a CGS unit. But what it is it's sort of 1 milli-Gauss is 1 micro-G, so 10 to the minus 6 of Earth's of 9.8 meters per second squared, Earth's mean gravitational field. So you can sort of see that the variations they are able to see here are at the level of 10 to the minus 5 or 10 to the minus 4G at that level. These are the variations due to mountains or valleys or sort of large scale sort of geophysical structures. Now, what we're interested to do with our experiments, is to really go much beyond that. So instead of looking at 10 to the minus 4, 10 to the minus 5, you can imagine quantum sensors have the precision to get down to the 10 to the minus 7, 10 to the minus 8 level. Then you can really start to see changes in water structure, water levels, for example, from tides. So the sloshing of the water level changing daily and over a longer period of time, changing in geological structures, earthquakes and so on. But really even beyond that, so looking at 10 to the minus 9, 10 to the minus 10, 10 to the minus 11 level, you can imagine looking at even finer structures, maybe changes in cloud formations, changes in water level and even at the surface. So this is really what's shown here on the right, which is sort of this idea of gradiometry. So instead of measuring Earth's gravitational field, you're measuring its gradient. This is in unit of Earths, which is 10 to the minus 9 per second square. So now depends on your baseline, but you can imagine that having a quantum gravimeter that can measure the 10 to the minus 9 or 10 to the minus 10, 10 to the minus 11, that would be the precision required to be able to look at changes in gravity due to surface and subsurface structures, for example. So you can look at changes in aquifers, water level, buildings, underground structured tunnels, all kind of interesting sort of features that are maybe not visible, sort of just optically. So that's what we're doing. Our experiments are still sort of lab-based for now, but we are sort of looking towards this more in-field applications. So we use interferometers. We're already familiar with light interferometers, and what light interferometers do, they use matter, they use glass usually, or beam splitters to direct light. So this is a famous example of a light interferometer, is the LIGO light interferometer. So the idea is sort of simple. You take a laser, you use a beam splitter to send it onto two different paths. The two arms of the interferometer are quite long, in this case 4 kilometers, but there's built-up cavities that make them effectively hundreds of kilometers long. You send the two light paths towards each other, recombine them on a photodetector and measure their interference as a light fringe. And these experiments are extremely precise, right? They can measure changes in the path length at the part per 10 to the 22 or even 10 to the 23 now level. And they're so precise that they can measure these tiny signals from these black holes that are tens of times the size of the solar mass. And they collide in a fraction of a second, and they emit more gravitational energy than everything else in the universe emits through ENM. So these are extremely sensitive devices. So that's sort of the idea, to do sort of similar physics, but with atoms instead. So this is an atom interferometer instead. It uses atoms as the wave, and then light controls the trajectory of these atoms. So I start with an atom, ultra-cold atom. You can sort of think of it as stationary in space. So it's really not moving. I use a laser pulse to split the atom onto two different paths. Then mirror pulse in the middle, a pi pulse to send the two paths toward each other, and then a recombination pulse at the end. There's two interferometer ports, S1 and S2. I measured those. I calculate this asymmetry, which is basically kind of like the ratio of the two. And then it turns out that is proportionate to the sign of a phase, of an interferometer phase. And you can see here, as I change this phase, I get these really beautiful fringes that can give me really good precision. Now, where does phase come from in an atom interferometer? Really, there's two main sources: propagation phase, which is from the fact that the atoms travel through potentials. You integrate that, the Lagrangian corresponding to that interaction over the classical trajectory of each one of these arms, and take the difference, and that gives you the propagation phase. Also, every time the atom interacts with a laser, there's a laser component. In any case, these systems can be extremely sensitive, so you can get precision at the part in 10 to the 9 or even a part in 10 to the 10. And this is why they've been used for different kinds of measurements. This is an example of a gravimeter that it can be brought around and used to measure gravity in the field. So this is a measurement in the Berkeley Hills that show really good precision. This experiment started in the lab first, right? So they were precision measurement devices to measure fundamental physics, such as the gravitational constant, look for fifth forces, look for measure the fine structure constant, and so on. So they can be really, really precise in the lab. And this is, I think, where we are with our current approach. One of the limitations in these systems is measurement time. So far, atom fountains are limited by at least on Earth, are limited by the time you have in free fall. So typically 10-meter experiments can go up to a few seconds of measurement time before the atoms splash onto the window of the vacuum chamber. So the approach has been to build taller, or you can use different approaches to increase this measurement time. It's zero-G planes, drop towers, sounding rockets, and so on. And Jason even mentioned we have these interferometers in space, right, in microgravity, and then you're not really limited by the same effects. Maybe there's other challenges though. Despite all of these experiments, right, there's still a limitation to a few seconds. So this has been sort of the maximum interaction time that we've been able to use these experiments to measure for, which limits precision. So this is where our approach comes in. It's sort of a little bit different. So we start with a sample of cold cesium atoms that are spin polarized. So you can think of this as the atoms moving in one dimension as a function of time. The beginning of this sequence is really similar to what a typical atom fountain would look like. So we use a sequence of 2 pi half pulses separated by time t to create an interferometer with 4 arms, in which there's 2 pairs of arms that are spatially separated by the same distance delta z. So we choose those 2 arms, we wait until they reach the apex of the trajectory, and then we turn on an optical lattice. There we go, and then they get loaded into that optical lattice. We wait for time tau. Hopefully time is very long, so we get really good precision. They accumulate gravitational phase, which is given by this equation here. It's basically just the difference in potential energy between the 2 heights times the interaction time. So it's sort of a simple equation to keep in mind. And then we recombine those 2 arms and measure the interference fringes, which are beautiful. And the maximum contrast here, it's about 50%, just because you have 4 arms at the end, but only 2 of them can interfere. So that's how our experiment works. This is the device in the lab. So it's sort of like just, the size of a little table here with some lasers that go into the vacuum system, and there's imaging systems and then coils and so on to control the magnetic field. But how well can we do? So I was saying that typical interferometers are limited to a few seconds, maybe. In this case, we don't even see any contrast loss for a couple of seconds. We can easily go to 5 seconds, 10 seconds, 15 seconds, even 30 seconds, and the record has been, seeing contrast or seeing coherence at 70 seconds. So this is the longest ever spatial superposition state. Really, it's bringing this quantum phenomena that typically have a hard time surviving at the, microscale, millisecond scale into the second regime, even minute now. And it's really an impressive sort of thing to see, just this quantum spatial superposition coherent state surviving for really this long. So we really did this, we wanted to use this in a measurement. So we wanted to see that this is a useful device. So we did a measurement that I mentioned on the first slide, which is to measure the gravitational field of this tiny tungsten source mass. It's about 1 inch length and 1 inch in diameter. So we put our atoms next to this source mass, we change their position above and below. We move the source mass in and out. So that's to reduce systematics and to improve the precision of our sensor. Here you can see the atoms moving inside the source mass at different positions as we use an atom elevator. I don't have much time, but these are the systematics. Everything looked good. There's really no issues. Everything was either understood, or we could was expected, or we could characterize really well. The precision of this measurement was 5 times better than any previous atom interferometer measurement. So we were super excited about that. This was the measurement result. So this is the measured acceleration due to the source mass. We compared that to the prediction from Newtonian gravity, and we see very good agreement that lets us put a limit on deviations from Newtonian gravity at this level with 95% confidence. And this allows us to put bounds on certain theories of forces that come from screen gravity. This might be what's required to explain things like dark energy, so why the universe is accelerating at a larger rate. So just in the last couple of minutes, I'm at the University of Arizona since October 2024. This is some of the lab and some of the people in the lab, and we've been having a lot of fun setting up new experiments to sort of achieve 2 goals. So the first goal is to build the next generation atom interferometer using an optical lattice. So we want to develop this method in new directions with new applications and sort of better precision and solving some of the issues we had previously. And then also we're very interested in building compact sensors that can be used in the field. So the new system will have many different changes, many different upgrades, many different sort of ideas that will improve precision quite a lot and allow us to achieve really interesting measurements of fundamental physics in the lab. So for example, we would like to try to measure the gravitational constant big G, again, with better precision. These are very challenging measurements that were done with classical sensors, and we think that quantum sensors can really help with understanding some of the systematic limitations, maybe, that are very, very hard to keep track of in a classical sensor. So this is the vacuum system where it was last year in May, and then we sort of finished it up in December. We've been building a lot of the supporting systems, optics, coils, magnetic fields, microwave fields, and so on. Most of the systems are complete, so we are starting to run our experiment. We have 2 main technical sort of results already that we've published. So we have this in-vacuum heat pipe cooled electromagnet that we wrote up in Review of Scientific Instruments last year. So we're really excited to start using this for evaporative cooling. And sort of the idea is using heat pipes to transfer the heat out of the vacuum system is a good way to reduce complexity and sort of make your system modular and compact and robust. We also have a mod that we just actually put a paper on the archive, and we're very excited to sort of look at this mod, which has certain changes from a traditional mod. The atom numbers are still very high, but we think the robustness and stability can be a little bit good, especially for a lab setup, right? So all of our systems are operational. We have an optical lattice atom interferometer already. We are still tuning things around, but really things are moving fast. So this was our first interferometer fringe. So our first measurement of gravity on the left, we got that in May, and 21st of May. So we're super excited to see that. We were only seeing coherence up to a hold time of 20 milliseconds then. And since then, in the last month and a half or something, we've already been able to achieve 4 seconds of measurement time and still see coherence. And I think this is actually the longest ever optical lattice interferometer that does not use an optical cavity to filter out the optical lattice. So we're sort of excited to see first, how well can you do without an optical cavity? Can you really get similar coherence, or is filtering the optical lattice really critical for this type of experiments? Very excited about the practical applications. This is a project that we're still to really start in earnest. We're still looking for funding, but we know that this optical lattice interferometer is robust to vibrations, tilts, and environmental magnetic fields. So this is something that we already wrote in a paper in my postdoc at Berkeley, and we've shown that these are practical advantages compared to free fall atom interferometers. And we're sort of looking to maybe take advantage of those by maybe building a small scale, robust, compact system, a proof of principle measurement. Maybe it's something that can fit into the back of a truck. And then you can think about, driving this around and then show that if you measure gravity in the field, might be useful for geology, geophysics, looking for underground types and structures, changes in underground water level, maybe even looking for mineral deposits and so on. And, what I mentioned at the beginning, and Jason, obviously described really well, is looking for changes in the gravitational field of the Earth from space. That will be super exciting to do. I'm already over time. This is the team that's working on it. We're a pretty small team, 3 grad students here at the University of Arizona. And in summary, I introduced atom interferometry as a quantum sensor for measuring gravity. I showed you a new way of doing atom interferometry by holding the atoms in an optical lattice. I showed you the longest ever spatial superposition state that I think I know of, which is at the coherent for 1 minute at this moment. Some of the measurements that we did to place bounds on new forces, on free forces, especially chameleon symmetrons, dark energy candidates like that. And then also some of the new recent progress at the University of Arizona, our first interferometer fringes, and now extending up to 4 seconds of coherence, and some of the plans that we have for doing more exciting science into the future. I think I'm already out of time. Thank you very much.
Thank you, Chris, for a wonderful talk, and congratulations on these great results. This is very impressive. We will again keep the questions for in 15 minutes, 9:30. And for now, I would like to invite our next speaker on the stage. Our next speaker will be Carlos Ortiz Marrero, assistant professor at Colorado State University and a joint appointee at Pacific Northwest National Laboratory and a PI at the Co-Design Center for Quantum Advantage. So Carlos is doing a lot of impressive things, and today he will share about quantum error detection for quantum sensing. So this should be interesting for both the algorithm people and the quantum sensing people. Carlos, please come and take it away.
So today you've heard a little bit more on the experimental side, which is good because that's the part that I am least familiar with. And I can probably go through those slides a little bit more quickly and get to the part that I'm a bit more interested in and I can contribute a bit more. So for background, I am an quantum algorithms person. So I come from analysis of algorithms. I did a lot of work on quantum machine learning, so more on that sort of computational side. And this project was an attempt to for myself, learn a little bit more about quantum sensing, because I kept hearing at P&L, quantum sensing is where quantum right now is being used. And I wanted to see how, with the knowledge that I had, how I could translate some of the concepts that I learned in quantum computing to quantum sensing and vice versa, to potentially kind of get a better understanding of where this advantage is really coming from. So this project was a result of a collaboration with Nathan and one of his postdocs. And if there's anything that you want to, I want you to get out of this talk is that little statement that I have there, which is basically that entangled sensing probes promise to achieve really, really high precision levels at the limits of physics, which is called the Heisenberg limit. But the issue is that noise is going to basically kick you back into the standard limit. That's the issue. What we're proposing and what we worked out in our work is there's some proposals that say you should just do error correction. However, the overhead on error correction for these sensing probes is really high. So we're saying, let's do something intermediate. Let's just error detect and post-process after the fact. Okay. So if there's anything that I want you to get out of this talk, that's basically the one-liner sentence. I am going to skip most of this because I think this was already covered by the two previous speakers. But just to say that, like, for myself, I was trying to figure out a good application where these techniques could be potentially applied as a way to propose a potential partnering of ideas, so to speak, in this workshop with people that are more familiar with the application side. And one thing that stands out for me, the idea to basically measure gravity very precisely, right? So we know that there are these like boxes that you can kind of carry around and measure, let's say, changes in gravity from, let's say, an underwater way in like a glacier, for example. I'm using that kind of as my inspiration, but only so that I can turn this problem into a problem in computation that I understand, which is called the quantum phase estimation problem. It turns out that this problem is just what we call in quantum computing quantum phase estimation. And if, you know, the names don't really matter, but what's useful is that once you can start attaching names, you can have all these like tool set that you can bring to the table to do analysis of algorithms. And by an algorithm, for me, what I learned is just a protocol. What you do to do some measurement and, or some evolution and some measurement and readout, right? To say that the interferometer that was talked about before can be translated in this way of measuring a phase instead. The fact that you have, like, let's say a 0 or a 1 just corresponds to basically some event taking place. So basically, when you're trying to figure out the property of what's happening in a momentum state, did a photon kick, let's say, that particular atom, or it didn't kick it, or sorry, did it kick it, or did it nothing happen? So those are the two branches, and those from a computational perspective we can think about as a 0 or a 1 event, right? And now, what's interesting about this is that this then translates our ability to read this out and analyze how many times we have to perform measurements over and over again. In computing, we call the Hadamard test, okay? And what the Hadamard test tells us, if you work out this computationally, is that you have very specific probabilities that you get out for 0 and for 1, and these probabilities correspond to changes in your phase. All right. And we can read those out and then do sort of some maximum likelihood estimation as to what is the most likely phase after the fact. Okay. So with that kind of framing in mind, here's basically just kind of a quick recap of what that looks like from a computing perspective. If you folks are familiar with quantum circuits, this is just basically the fact that you're putting your state in superposition, then you're exposing your state to the signal, then you're doing a readout. That's exactly, you know, the Hadamard test from, like, you know, a quantum computing 101. And then the trick is to be able to, how many times you have to perform this to get up the position, their desired position. What we can do now is that we're kind of at the standard limit, which means that if you want to get a tolerance of epsilon, you have to roughly sample 1/epsilon squared, right? And this grows pretty fast, right? As you can see in this chart, that's not a desirable outcome. We would like to move past that. And just kind of, I did some kind of back of the envelope calculations here to kind of ground myself in the application here, and to kind of give you an idea of how the numbers compare. With the current techniques that we have right now, we need about 3.9 times 10 to the 5 atoms roughly to reach a position of where we're at, kind of at the state of the art. But if we could do something in an entangled state instead, we can reduce that number to something significantly smaller, like 621 or so. Now, this is assuming that noise is not seeping into your calculation, which is obviously the difficult part. But there is a protocol where you just can entangle your probes. Your probes will all get exposed to the field all at once, and you perform a readout. The readout then gets you to the Heisenberg limit effectively, and that's why that reduction occurs there. As I said, I'll make these slides available for folks who want to see more of the details, just kind of give you the rough story. But here's the kicker. The kicker is that as you start introducing noise into this GHC or entangled state, you need more and more to be able to combat the noise that's going to start seeping in. At some point, that defeats the purpose of the whole planning the experiment because the noise is going to kill you. So you need to figure out a way to combat noises. Some of the people have proposed is to use error correction. So you can kind of create a probe, and inside your gravitometer or whatever machine that you're using to measure your phase, you basically engineer a sequence of gates to perform error detection and error correction. And there's a whole slew of literature on this that people have been looking at. However, what we proposed was more thinking just about what can we do with error detection? If we just restrict ourselves to just error detection and we try to think about how to implement those in the actual devices as opposed to full-blown error correction, how far can we get? It turns out that we can get really far. This is just a quick caveat in the sense that, like, you need an entangled probe if you actually want to achieve this Heisenberg limit. This is another thing that we ended up doing a little segue in our paper to show that you needed this. But to get back to the detection idea is that what you do is that instead of just looking at just the zeros and ones, what you use is use the information that you were getting from the syndromes, from what happened during that process of the computation, right? Can you perform a syndrome measurement, which just corresponds to a sequence of gates, which is much minimal than like what you would need for complete error correction. And then you keep track of what happened, that event. And then what you do is you put that into your likelihood estimation function, and you weigh less if a lot of errors occurred, and you weigh more if less errors occurred. Effectively, that's what the protocol boils down to. The rest of our paper was just really showing that this gets you to Heisenberg-limited scaling and all the math that comes with that. So yeah, so effectively the way the protocol works to maybe give you more the step-by-step ladder is what you do is you first set your state, let's say, to like some GHC state. What that just means is some entangled probe. You're going to do some syndrome measurements. Detection, not correction, and then you're going to accumulate all of that data into your estimation procedure. And there's a lot of cool stuff you can prove mathematically, which is something that we were really interested in and wanted to do, in that we definitely proved that as you increase the code length of your GHC state, so as you have more and more probes, the error that you can correct or that you can detect, decreases exponentially, which is something that you want for a desirable protocol. We've also done some numerical simulations to make sure that, like, you know, what we actually propose has some nice sanity checks. So in particular, we show that we do indeed get some form of a Heisenberg limited scaling. Is not as perfect as what you would get with a pure probe, but we won't, it's unlikely that we're going to get a pure probe. And this is where I kind of wanted to get to and make sure I don't forget that I think there is possibility with this protocol to propose some pilot study where you can attempt to recreate these detection gates inside what we currently have. And the technology is already there because neutral atom quantum computers, for example, are pretty advanced, and they're using a lot of the same techniques that folks use for capturing atoms and doing interferometry. Yeah, I'll just leave this here, food for thought for folks to maybe, as you see me around in the workshop, bring up some questions, and I'm happy to learn about The community, as I said, I'm kind of new more to the community. I'm more from an algorithm side, but if you have any questions about quantum computing and my foray into sensing, please let me know. That's a link to our paper. And a quick shout out that at Colorado State, we're doing a hackathon. Part of something that the first speaker brought up was the fact that we need to kind of promote more of this like workspace, workforce development. So we'll be hosting this in August 22nd, 23rd. So for those of you who are local, please spread the word. And I'll probably leave it there. Thank you.
Thank you, Carlos. Fantastic talk. Very inspiring to think about to which quantum sensors we can apply this and how it can really advance applications. It is now finally time for questions, and I would like to invite Jason back on stage at the table here, and also Anarita, our co-chair of the session, to take a seat here at the table. Cristian, please stay on virtually. I'm sure there are many questions for you as well. And with that, the stage is open for questions. If you have a question, please come to the microphone. Our first question is there.
Hi, Matt Heyman at NCAR. One of the challenges that I have when we talk about quantum sensing is what on earth we're even talking about. Jason, your example, you kind of kicked it off. It sounded like we were talking about Bose-Einstein condensate. The example talks sound like we're talking about BEC or quantum entangled state detections. But then Jason, in your summary slide, you had photon counting LiDAR. I work on sensor development. We have a micropulse dial. It does photon counting. It uses DBR and DFB lasers, all based on quantum technology. We're interrogating states of absorption lines in water vapor and oxygen, which are all quantum predicted. They don't exist in classical mechanics. So is that a quantum sensor? Like, it's not clear to me what we're even talking about.
So it's the common question I get from every audience. It's like, I have a micro kinetic inductance detector, or I have a single photon detector. I have an integrated photonics. I have a DBR lasers. I have a quantum gravitometers. I have a LiDARs. Are there quantum sensors? I think whatever you want it to be is the answer. So we don't have a clear definition of what is a quantum sensor. If you're manipulating atoms or molecules or photons in a way to detect a particular measurement, we consider that as a quantum sensor. So that's what the current understanding is. So we don't want to be very exclusive in a way that, like, if you're not doing this, then you're not a quantum sensor. Rather, we want to promote all the different sensing capabilities as much as possible. And quantum sensing, using manipulating atoms and things like that to do a sensing is a new way of, as a part of the quantum sensors, but we're not trying to associate other modes of sensing capabilities. As long as you're manipulating photons or atoms, we consider that as a quantum sensor today.
I mean, that presents a challenge, right? Because we're talking about 30, 50-year legacies that are now quantum sensors. They were just never marketed that way before.
Right. But then, quantum theory exists 100 years. Rydberg sensors that I told you about, the Rydberg concept existed 50 years. The only reason why we're doing it now is because of the advancement of the lasers and the techniques. Otherwise, the concept itself, it exists for, tens of years.
And some people distinguish between kind of the first generation or wave of quantum, which was 50 years ago, including the invention of lasers. And now there is a second wave where we can not only detect photons, but even single photons. And and we can work with entanglement, superposition. So
Yeah, Vivek from NCAR. I have a question on the Rydberg quantum sensor. You mentioned about that. You mentioned about the broadband, you can tune it to many microwave bands, you can use that. Could you comment on improving the sensitivity in the low noise amplifier in the front end of any radar? So wondering, could you comment on improvement, because thermal noise versus photon noise, we're talking about kind of noise exists whether you have Rydberg or LNA from, could you comment on that?
So the key benefit is not on the improvement of the sensitivity. The key benefit is improvement of broadband sensitivity. So you can measure multiple microwave signals with a single receiver. But as far as the sensitivity in terms of LNAs, amplifiers, the heterodyning, all that aspect is pretty much the same, the way I see it today. I'm sure it will improve at some point, but the front end is same antenna as the traditional radar antenna. So, like I said, only the receiver is the Rydberg cell that's going to be receiving that signal and translating to a particular microwave signal. But as far as the whole processing chain is very similar to the traditional radar.
Okay, thanks for that. Following up with the Rydberg sensor, is that be customized each time, or it should be available? Like once you have a design, someone could make this one within certain time period. How does it work?
So it uses a receiver. So like so it's real time. You could switch between the different frequency. So Ka band, and then I'm detecting L band signal. I can switch. So you could just excite the energy of the rubidium or cesium to a particular rubidium energy Rydberg energy transition, and then you could detect that. So you're switching this in real time.
Yeah, thank you very much. So firstly, so my name is Junyu Liu. I'm an assistant professor of computer science at the University of Pittsburgh. I work primarily on quantum machine learning, but I also very interested in work a bit on quantum sensing. I have a question and also a comment for Jason that regarding the definition of quantum sensor that we have discussed just now. So like I think there are some literatures that call firstly, if you have a qubit and then you do some measurement, it's called a type 1 quantum sensor. And if you have some coherence but no entanglement, it's called a type 2. And then if you have both coherence and entanglement, it's called type 3. And then actually in one of my work, I define a type 4 sensor to be a combination of quantum sensor together with quantum devices, quantum computers. There indeed exists a various definition of quantum sensor, and then there are some unified classification of them that people have done before. My primary question is also along with this line. So I think I feel that the experimental efforts that we talked this morning and the theoretical effort is a little bit disentangled in the sense that it seems that in the talk that experimentalists primarily describe they are type 1 and type 2 quantum sensors. But for type 3, where Carlos was talking about in his talk, I didn't see direct evidence from the experiment. Maybe it already have done, especially in extreme conditions like a satellite or some other places. Entanglement are very fragile. They are a demonstration of Heisenberg-enhanced sensors in the lab, but I don't know, from Jason, your perspective, how far you think they can be potentially deployed in an extreme condition or in some earth science or weather or climate science kind of task. There are proposals in theory, but I think experimental side, I was wondering if NASA is interested in such direction, or if you think it is too far from reality. Yeah, this is my question.
Those are two great points. I think based on the comments that you have provided, I think we need to define different types of quantum sensors so that when we are talking about particular concept, we know we're talking apples and oranges, and so to speak. So I think as a community, I'll take that as a feedback and try to define what those are. If you remember the quad chart I showed you in terms of classical sensing, manipulating photons, manipulating behavior of the atoms, and then the ultimate is the quantum computing that manipulates both aspects of it. And so that could be different types of a classification of a quantum sensing activities. As far as the entangling sensor is concerned, we are very interested in that concept. And as Carlos said, in theory, you get the true effective N but there's a lot of errors. So this work needs to continuously improve. But as far as NASA is concerned, spaceborne constellation, I think the key variables in the climate is concurrent measurements, right? You need to do multiple measurements at the same time rather than one delay by every 16 days because of these satellites. And then also spatial coverage, right? In terms of you want to have a high spatial resolution. So I think the entangling these sensors is going to be critical, but I just don't see it happening in near term. But what I'm saying is you can't just wait and see what happens. You got to continuously work on it to getting towards that architecture. So building a architecture based on quantum sensing is another aspect that we need to focus on.
I see. Thank you very much.
If I can maybe add to that, I think the level of quantum control needed to achieve those goals, especially entanglement in a useful way, it's sort of very challenging, honestly, right now. And the methods, especially in AMO, atomic molecular optics physics, has have been improving over time, and I think we are getting close to that. There's examples in atomic rocks, for example, in which they are very close to the more traditional sort of unentangled sensors, so that the entangled sensors are getting very close. There's examples in magnetometry, for example. But yeah, I think it's a matter of, as Jason said, just improving technology and getting it to a point in which you can just get enough quantum control to be able to achieve those goals, to get entanglement to be useful in your quantum sensors.
I see. Thank you.
Hi, I'm Brian Mapes. I'm an atmospheric science professor in Miami, just patrolling widely here. I'm learning a lot from Wikipedia and you all this morning. Looking for anything might be practical in my lifetime that comes out of all this. And one thing you mentioned that I don't understand is you used the word uncertainty quantification. I understand the microgravity and that stuff like this. What does uncertainty quantification mean? Do you mean down in the nano space getting precise, or do you mean this will help in some kind of earthly uncertainty quantification about the atmosphere or ocean or something?
So I was mainly talking about the modeling errors in terms of how much uncertainty is built in your prediction and forecast. So that's what I meant. So in order to reduce the uncertainty, you need to increase the measurement, you need to increase the sampling, you need to increase the algorithm itself in terms of accuracy of these algorithms and computing. So all four are needed in order to reduce the errors in order to have a better prediction and forecast. So that's what I meant by uncertainty quantification, how much of uncertainties are there, and can you actually quantify those errors more reliably?
I see. Pretty straight ahead definition there. It's not about quantum chaos, teaching us something about chaos. No. All right. And this word noise that creeps in, I wondered if new kinds of noise here might be showing us how noises interact with signals or anything. Or this is all very more earthly, practical.
Yeah, so from the
measurement is good because it makes us more sure about what's real in the world. Is that all
right? So from the perspective of when you're thinking about an entangled probe, noise here is hard to kind of distinguish from signal, actually, it turns out. So it just depends on what you're trying to measure. And in some of the cases that we analyze, so for example, we were trying to measure a specific parameter from one of a particular polygate, and then the other one is treated as noise. So we usually make assumptions as to like that particular term in your evolution of your Hamiltonian is small in comparison to your noise, and sorry, in comparison to your signal. That's what we mean by noise in this case. But that's more like on the specific nitty-gritty of just analyzing the actual protocol. But noise really can be anything. It's basically anything other than what you want or what you care about. It's what we usually think of noise. At least that's how I treat it in the protocols that I look at. So yeah.
Yeah.
Hi everyone, thank you. Ruben Demerjian from Naval Research Laboratory. I had a question for Carlos. So I found it really interesting that you're coming from quantum computing community going into quantum sensing. And it seemed like that your contributions were, if I understood everything correctly, mostly in error correction. But I'm wondering if there are other contributions the quantum computing community other than hardware, more on the algorithm side that we could give to the quantum sensing community.
Yeah, so I think what we mostly worked on, as you said, is applying error correcting techniques to basically reduce the overhead that you would need. But in the paper, we actually unified this protocol as there's a generalization that's called quantum signal processing. And if you think about the probe as being some encoded qubit, what you're really doing is you're applying that particular primitive to the encoded qubit to be able to then basically create the activation function that you care about to read off the signal that you want. So I think this is a really new field, is kind of what I've noticed. And the advantage for me, at least, well, one, it was familiarity to translate it to quantum computing, but also quantum computing has really thought about algorithms for a long, long time because they're seeking advantage so like heavily, right? And algorithms are just basically protocols, like as far as what I've been able to perceive. So it's new. I would say one thing that I would recommend to check out would be the quantum signal processing protocol. I think that's another primitive that I think there's a lot of inroads to going down and get interesting results that we only started scratching the surface. Yeah.
Yeah, thank you. It's amazing. Quantum signal processing has so much utility already, so there's another application for it. Thank you.
Hi, I'm Swamit from University of Wisconsin. I have my first question is for Carlos. So when you're modeling noise in your protocol, are you assuming like standard error correction depolarizing noise? Is that like a realistic depiction? Because I think the quantities that we are dealing when we are sensing are entirely different than when we are computing, right? So I just wanted your thoughts on how we should model noise.
So the issue is that there is a specific condition that you have to satisfy called not in the Limbladian. And effectively what this means in the cases, I'll give you kind of more of an example. If you're trying to look at the evolution of a Hamiltonian that has a Z and an X field, in that particular case, the non-Limbladian condition gets satisfied, in part because X and Z are somewhat orthogonal. If you introduce Y, the protocol no longer works, but it's because it doesn't satisfy this condition. And this condition is a necessary insufficient condition that was shown, I think, in 2018, I want to say, by Preskill and another group. So right now, from the algorithmic side, the current, we're more trying to figure out what are those necessary insufficient conditions to then maybe try to steer the rest of the noise in a different direction, right? Algorithmically, if you don't satisfy this condition, you just can't measure, you can't achieve Heisenberg-limited. You can still do sensing. It's just that you won't be able to hit the Heisenberg-limited limit that you want. And I can point you to maybe some more details if you're curious about seeing about that. But depending on how you look at the problem, dephasing, for example, might not be included. Yeah.
Thanks. My second question is for Jason. I think, again, thanks for a really amazing talk. You primarily talked about two sensors, I think, one microwave sensors using Rydberg atoms and other, atom sensors for measuring gravity. So as far as I understand, there is an imaging that is required. And it turns out it's kind of slow. Like if we are using EMCCD cameras, QCMOS cameras, they're pretty slow. And even the neutral atom computing community is kind of struggling with the speeds. So does that mean that we will be bandwidth limited when we are sensing these quantities? Is that a problem?
So, working jointly with NIST, we're building these 2D array imaging capabilities. So SNSPD, superconducting nanowire single photon detectors that we're developing, we're trying to achieve like 2K by 2K array cameras. So I think we are advancing, but like I said, the back end in terms of readouts, those are not pure quantum in a way. So we're coming up with some innovative ways of doing a large scale readout technologies for cameras. And then also, ghost imaging and other techniques that we can also apply on top of it.
Right. So I think there is a growing need for high-speed cameras, especially when we are doing atomic sensing or computing applications. And there is this SPAD cameras. That's kind of really interesting and emerging. I'm just curious if you are considering those high-speed cameras where rather than getting a pixel, rather than getting an intensity, you get just photon counts. It's very close to SNSPD, but like a lot of our iPhones, for instance, use these cameras for low light conditions. So I mean that might be really interesting as well. Yeah.
Yeah, like I said, I think those are something that we'll be very interested in looking at it. NASA traditionally are building capability for remote sensing has to be in space related, but airborne sensors, in situ sensors for these type of activities, I think NSF and NIST and some of those organizations might be very interested in pursuing it.
Thanks.
We actually have an online question, so let's go to Junyu Liu. Feel free to unmute yourself and ask your question.
Hi, Jason. Thanks for the amazing talk. So this is Shan Zeng from PNR, and my question to you is that so the entire community, including the classical dynamics community and the quantum computer community, as Carlos also put it out, has been really trying hard to find the killer app for quantum advantage. So my question is that in terms of the quantum sensing, what's your take on a few of those really killer apps that we could achieve in the limited funding and time frame work in the coming, let's say, 10 years or something, such that we can demonstrate, okay, with this, we can basically reach some kind of realm that your classical sensing cannot really reach.
So, I talked about the QGG and the Rydberg microwave sensors, but also, we're developing clocks, and then also we're developing magnetometers, and those are kind of the initial concepts. But in the future, there could be quantum radars and then lidars using these entangled mode in a way that you detect a thermal signal and then be able to detect those visible by entangling the incoming photons using lidars. Thus, you can very minimize your overall payload because you don't need a cryocooler to cool the detectors and so forth. But as far as the killer apps concerned for sensing, the most near term is the atom using atom interferometers to detect gravitational potentials and force. And there could be many different applications you could apply, detecting tunnels, mining applications for science, exploring ocean worlds and ice giants in terms of you want to see what's underneath, and variabilities for lunar exploration, like I said, in situ resource utilizations, habitable tunnels as for astronauts and so forth. So I think the QGG and the Rydbergs are the most near term. I could see something in operations within 3 to 5 years, both from the airborne and the spaceborne applications.
Thanks. That is really promising.
Yeah, so hi, I'm Brian Vanderwend. I work at Quantinuum now, so I'm definitely coming at it from the quantum computing side of things, but worked at NCAR for a number of years. I was just curious on the quantum sensing, on the instrument design, like this question was motivated by Christian's one slide where there's the interferometer on the van. And I'm curious what the biggest technical challenges are when you are designing these instruments. Like that made me think about vibrations and how difficult it is to control vibrations in our quantum systems. So what are the biggest technical challenges that are faced on designing the sensors?
Yeah, that's a really great question, and this is something that we've seen in the past, right? You build these things in the lab and they work really great, and then you try to put them outside of the lab, and there's challenges that come up, right? And at least for atom interferometry, we are sensitive to motion, right? They measure acceleration. They are designed to do that. So that means that acceleration from vibrations will also be an issue. So something that I think, it's sort of been a goal is to find a way to isolate this quantum sensors. So they typically, maybe you'll have a vibration isolation table or maybe now you have a magnetic shield, right, to sort of protect your quantum sensor from this sort of noise that comes intrinsically with operating outside of the lab. Sort of our approach has also been to try to find different types of quantum sensors that are maybe not quite as sensitive to this factor. So this is what that slide was trying to do, really, to show that this optical lattice atom interferometer intrinsically is less sensitive to these effects. You know, one sort of simple example is, you know, just the atoms don't move as much, right? In an atom fountain, they'll be falling over maybe a few centimeters, tens of centimeters, maybe even a meter. In this case, you know, they're really in place for, you know, they're localized of a millimeter, basically. So, you know, just isolating magnetic fields, for example, is much easier. The other advantage is with vibrations, since the optical lattice is holding the atoms in place, this vibrations instead of just aliasing, so the atoms only see the vibrations when they interact with the laser pulse. Now, the vibrations kind of average out. So, you know, the arms of the interferometer moves together for a long time, and that averages out vibrations. So this has been sort of the goal, to find sensors that are less sensitive to the environment, but also find ways to sort of, you know, isolate those effects too. So going from many different directions. Did that help? Did that answer your question?
I could add a little bit more. I mean, I could spend a whole day just talking about what the key challenges are. So, you know, building an atom interferometer, you need to generate a lot of number of atoms. You know, we're talking like millions and you know, tens of millions of atoms at the initial prep stage, and then, you know, if you have a lot of atoms, your cloud gets bigger, so it's a lot easier to build interferometric measurements. So that's one issue. You know, if you want to use heavier atoms like cesium over rubidium, it's a lot easier to also manipulate, but then you need to have a laser that's going to be tuned to that particular cesium. For instance, 780 nanometer for rubidium, we're using it because there's a lot of COM lasers that's already been operational, so we're just frequency double that lasers to manipulate it. But for cesium, you need 850 nanometer, and that has to be built from the scratch. So you need to you know, build a laser that's tuned to a specific frequency. In terms of you know, flying in space, the thermal noise is very critical. It's like the variance of the thermal variation has to be less than 1 Kelvin. So maintaining that environment is very critical. So it's not just the sensor itself, the spacecraft itself has to be very stable. So that's the key efforts that we're focusing on right now in stabilizing the platform. But as far as the vibration in space, because it's atom, you know, it's a two sets of atoms, so vibration, it cancels out normally.
Hi, I'm Aman Gupta. I'm a research scientist at Stanford University. I had a more applications-oriented question. You mentioned these broad range of applications, how you can use quantum sensing, these interferometers to measure gravitation, changes in gravity, and then connect it to climate signals, right? But I realize that most of these applications were focused on understanding the mass distribution at the surface. I was wondering, can the same sort of advances be used to measure like rapid, like non-hydrostatic changes in the atmosphere itself, like convection, chemical species, or, you know, gravitational separation, things like that? Is JPL working on that, or does it present like a fresh set of challenges that were not discussed today?
Yeah, I mean, I'm sure, you know, we're using radars and LiDARs today to look at the aerosol cloud interactions, precipitation, and then the convection processes in the clouds. I think those techniques are viable. We haven't even launched these sensors yet. So let's do the classical one first, and then try to figure out where the gaps are, and then maybe, you know, how quantum sensor can replace it. But I think the most critical thing is how can we fly LiDAR and radar together to fully understand the convection processes.
Hello, so my name is Leo, and then I just entered at NCAR this summer. I wanted to ask Carlos about your research. So specifically on, I think you said that your technique was mainly on error detection. So then I was really curious about after you detect the error, how do you do the post-processing? Is it via like classical computers or quantum computers? Especially if you can't recover the initial quantum, I guess, wave function.
Yeah, that's a great question because you would think that once you measure the syndromes, there's going to be some sort of collapsing that happens. Indeed, it does. You measure the syndromes, you capture that data, and then you capture the bit that you got out, and you keep that data stored. And then what you do is maximum likelihood estimation. So it's all classical after the fact, which is also helpful because you just have to, from how I understand from an experimental perspective, it's a little bit just easier to just capture all this data and then offload it and then post-process it, as opposed to having to do error correction, which requires like active control and feedback loops that might make everything much more complicated. So this is just you do a full pass, you capture the syndromes, you capture the bit, and you store that and you post-process it. And that's all you have to do.
A quick follow-up question is, with the maximum likelihood estimation, is there sort of like a threshold of like noise to signal ratio that you sort of have to be below in order for the post-processing to actually, I guess, work?
Yeah, absolutely. Yeah, there's definitely like I think in the paper we gave sufficient conditions for this to work. But yeah, you definitely need those. Otherwise, like the issue really boils down to you can't really resolve the signal from the noise if your noise is too high. Really, that's kind of what starts to happen in some of the protocols. So there's a condition about a ratio between the strength of the parameter that you're estimating and the underlying signal underneath it that you can impose on the protocol, and then you would get Heisenberg-limited scaling after that.
Thank you.
Yeah.
We have one last quick question in person and Kelvin Drugemeyer virtually. If you still have your question, please after that.
Hello, my name is Shrikant. So here we are for the quantum computing because the classical computers are struggling with the petabytes of classical data from the sensor. So it is a curious question. So since we are struggling with the classical data, we have quantum sensors which are more accurate, faster than the classical sensors. So how much data you are getting at the NASA from the satellite sensors or the gravitometers?
The amount of data is similar. So, when because we constantly have to think about downlinking that data to the ground. So the amount of data that we're acquiring using a quantum gravity radiometer versus the GRACE mission, the bandwidth and the data is about the same. In terms of it's all really regarding to sampling, right? In terms of how much we want to take the data.
Okay, and my question is for Carlos. So since we have edge computing for the classical sensors, which will clear out the noise from the sensor itself, from the satellites or any sensors on the Earth, can we do edge computing for the quantum sensors using the quantum algorithms?
So this is where it starts to get a little bit tricky, I would say. So in my experience, in my whole years of working on quantum computing, the main unifying observation that I've seen is that quantum algorithms lose their advantage as soon as you measure. So like when designing systems or protocols for that matter, you need to be very careful as to not to introduce any sort of feedback loop into your process, a classical quantum feedback loop, because this usually kills your advantage. This is the most famous story, I think it's from quantum machine learning, which is the field that I was working on a couple of years ago, where one of the candidates was variational quantum eigensolver. Everybody was excited because you can put it on a loop, right, and tune parameters and compute gradients. But then what we ended up seeing is that for the Hamiltonians that you care about, the ones that you can classically simulate, the loop, you can't compute gradients because the landscape is flat. It's a phenomenon called the barren plateau phenomena. And I've seen this pattern, not just in QML, but in other fields. So topological data analysis is another sub-primitive of algorithms that have advantages or provable advantages. But papers have come out saying as soon as you introduce any sort of classical loop, the advantages just disappear. And this goes under the name of dequantization, in case you're curious to look more at some of these algorithms. But there seems to be some, to me at least, like enough evidence to say that the one thing we really want to avoid when incorporating any sort of edge device is that we don't incorporate a classical quantum loop into it, because it's most likely not going to end up working from what I've seen. Yeah.
Yeah, that'll be all. Thank you.
Right. So with this, it's my pleasure to now moderate a panel session on quantum sensing. And I would like to invite the esteemed panelists on stage. We have Dr. Jason Hyon, Chief Technologist for Earth Sciences and Technology Directorate at NASA JPL. Jason, if you want to please join me on the stage, thank you. Then we have Dr. Caroline Alden, who's Chief Scientist and co-founder at Longpath Technologies. And we have Dr. Wally Lawal, who's the Chief Technology Officer and co-founder for Mesa Quantum. So please give our panelists a round of applause. Thank you so much. So just to kick off the panel, maybe we can have each of the panelists describe the quantum sensing modality that you are focusing on, and maybe talk about how that quantum sensor is improving the classical state of the art. So Wally, do you want to start?
Yep, thank you for inviting us over to talk a little bit about Mesa Quantum. Pleasure to meet you all. Again, CTO, co-founder of Mesa Quantum. We focus on chip-scale atomic sensors, dominantly chip-scale atomic clocks, and advancing the use cases and integration for GPS resilience and several other applications. And so one of the big efforts in miniaturized low swap atomic timing solutions is how can they be used to advance emerging challenges and emerging needs. Some of those that are maybe unrelated to or not uniquely related to climate and weather might be just autonomous systems in general. That is a big emerging area that you tend to find use cases in austere environments. One of those in particular is, for instance, underwater applications. That could be via Scripps Oceanography or Woods Hole, who does a lot of climate monitoring, and they do long duration monitoring, maybe months, sometimes years of operations. And so as soon as they integrate a component in there, they're pretty much stuck with that performance until the duration of that operation. And so the better you can have a high performing low swap atomic clock integrated into those nodes under the seabed or in their array of sensors, then you can maintain good quality time tagging and data collection over the duration of those monitoring events. And so there's a lot of interest in to continue to advance how we collect sensor information, not just sensor arrays, but maybe a network of drones that are kind of autonomously navigating throughout the seabed. And how do we continue to help keep them synchronized and both from a time synchronization and data exchange and communication. And so there's a lot of those areas that really need precise timing to be able to maintain those type of synchronization events. So there's a lot of areas there that we are, continuing to advance. Another big one tends to be LEOSat applications, where that's become an emerging field, either from a GPS or a PNT capability, but then as well for lots of observations. So, hyperspectral imaging is an area that seems to be emerging in the LEOSat domain. And how do you continue to think about improving not just synchronization between those LEOSats and say GPS, but also the resolution of the quality of the data that you're getting. A lot of times being able to have accurate clocks help you with your radio occultation, where you're trying to precisely understand how those radio signals are navigating through different atmospheres. So those are two. I'm sure we'll have more conversations, but just wanted to kind of start to kick that off when it comes to timing solutions. And I know they'll talk about other modalities, but we focus on warm vapor cell atomic devices and how do we bring them into new emerging markets and solve some of these relevant challenges.
Hi, Caroline Alden, co-founder and chief scientist at Longpath Technologies. And I'm excited to be here with the director of ARPA-E because we were an ARPA-E funded technology initially at the University of Colorado, Dr. Greg Rieker's laboratory. He's the laser diagnostics laboratory, I think is what it's called, received funding in 2014. So hopefully this can be an inspirational tale of a crazy idea in a laboratory taking quantum sensing from NIST to University of Colorado all the way out to oil and gas fields, where we are also performing sensing of atmospheric constituents. So What we do at LongPath is we put lasers in the oil field to look for methane leaks to the atmosphere. So this is kind of the biggest low-hanging fruit in terms of greenhouse gas emission mitigation, is catching leaks of natural gas, which is 95% methane from oil and gas infrastructure. So we look for the methane signals in the atmosphere along long open beam paths, and I'll kind of get into the technology itself in a minute, but I just kind of wanted to paint the picture of what we use it for. And so we're sending the laser light out over long multi-kilometer beam paths through the atmosphere, reflecting the light back off a retroreflective mirror, and then getting path averaged concentrations of methane gas. And in your imagination, apply this to every other atmospheric species, because as we continue on this quantum advancement, many more molecules will be sensible. But so we've got these atmospheric beam path measurements of methane, and then we perform atmospheric inverse modeling to understand the sources of methane in the field and kind of pinpoint where the leaks are coming from. And actually our end user is the oil and gas client themselves. They receive the data. We analyze the data for abnormalities in the emission rate off a given well site and send them an alert or a note to say, hey, the emissions on this site are trending up, or hey, you've got a sudden leak event on this site. And then they can get out there, perform those repairs, and rapidly mitigate the methane leak to the atmosphere. So that's kind of topically what we use this technology for, and what ARPA-E afforded the transition of an instrument that was at NIST in 2012 and was so sensitive that you could barely close the door to the lab without the combs unlocking, to now you have the ability to put these systems in extraordinarily rugged environments where they run autonomously year-round. We have a system in outside of Fairbanks in Goldstream Valley. It's been measuring permafrost methane fluxes for several years now autonomously. And so the sky's the limit. And I'm excited at this workshop's capacity to inspire people to find those cool new tools in the lab, and let's get them out in the field. So a little bit about the technology that LongPath was founded on. It's called dual frequency comb spectrometry. And so in 2005, Jan Hall at the University of Colorado received the Nobel Prize for frequency combs. And what it is it's, and I'm not a laser spectroscopist, so you don't call me out on my errors, or do, but it's akin to 10,000 or 100,000 perfectly aligned and locked together continuous wave lasers. So you're solving a handful of issues with traditional sensing, which is you're achieving broad bandwidth. So you're getting potentially 100 nanometers of wavelength that you can cover with extremely fine spacing in individual wavelength ranges. And that's why they call it a comb. So it's these little tiny comb teeth. Each are probing a different wavelength, so that you can address multiple different wavelengths to look at those the low vibrational states of molecules like methane, and not just pick one wavelength where methane absorbs infrared light, say, but a whole broad, you can cover multiple absorption lines and actually get the full resolution of those absorption lines. And so the other kind of traditional problem that the comb solves is by having the wide bandwidth and the high resolution, you're able to resolve not just methane lines, but water vapor lines, CO2 lines. So you're not kind of guessing about your interference from other species, but you're actually measuring that directly. And so then at NIST, they took the single frequency comb, which was really neat, but there was no detector that could effectively read out and differentiate between the initial comb or all of the different comb teeth. And so they combined two frequency combs together to make a dual frequency comb, and they offset the comb teeth slightly so that a beat note arose. So like if you're tuning a guitar and you interfere the tuning, you'll hear a beat note arise. And so that is now readable in the RF on a simple photo detector. so that you can send out this incredibly resolution array of light across a broad bandwidth and then actually read the interference signal, which will capture all of those absorption of all of your molecules of interest in that on a simple photodetector. So I'll leave it there and pass it over.
Sure that you're sick of me talking, so I'm going to try to be short. So, from our lab perspective, we're mainly focusing on remote sensing and then also miniaturizing and adapting your instrument for spaceborne environment. So those are the kind of two key areas that we're emphasizing. So, obviously JPL, sensors are us in terms of any type of sensors that you want to fly in space. We're very interested in partnering and advancing these technologies. But as far as the climate science is concerned, there's a word, somebody said, observe globally, monitor regionally, and then act locally, right? So in terms of how you mitigate particular climate mitigation approach is concerned. So JPL's emphasis is on observe globally aspect of it. In terms of remote sensing, you do global changes, ocean circulation, ice mass change, aquifers, ocean surface winds, current measurements, ocean mixed layer depth. Those are the kind of key parameters that we want to provide as a global measurement. And then hopefully, agencies like NOAA or NSF will provide the in situ measurements or regional scale, like the ocean observatories that NSF runs. So those are the ones that provides the consistent measurements. And then by combining the global scale measurements with the regional scale measurements, you try to use that information to act locally in terms of how to mitigate flooding, coastal erosions, greenhouse gas, air pollution, things like that. So that's where JPL's niche is, and we're continuously advancing those technologies.
Thank you all. So the next question is, can each of you speak about the biggest technical and non-technical challenges with these sensors? And Caroline, as you mentioned, for ARPA-E, we are very interested in bringing the technologies from the lab into the commercialization space. So what are the barriers to that? Is cost a big issue? Are just the technical challenges, as you mentioned, closing the door, you have, signals that impact your, sensitivity and so on. So how do we make these sensors, more commercially deployable, and both from a technical and from a non-technical standpoint? And Wally, if you want to maybe start.
Yeah, so I'll kind of try to lump them all together. And I think, these folks can probably relate. I say a broader theme that I find is the lack of focus on fielded trials and demonstrations and using that to mature the tech development. I think we get so excited about, what quantum can bring that we end up funding advanced research, which teeters towards what we call basic research, more than we focus on transitioning commercialization efforts, where, even if it's a clunky lab prototype, you still take it out in the field, you test it, and you do multiple tests across different industries, different applications, and you understand where the real challenges are. You do that over and over and over and over again. I think the MEMS industry, for me personally, I feel like they got it right. They were very clunky and crappy, and and nobody really wanted them. But several decades later, they're starting to really perform at a very high level, and they've solved significant challenges when it comes to TempCo and sensitivity to environment and shock and all other aspects of manufacturing and yields. And they've just been able to apply a lot of focus because they were immediately deployed in the field in a way that allowed it to understand where it's going to kind of be hindered. I think what we demonstrate in the lab often is just really hard to translate into a fielded environment. And so that's one big thing that I think is a barrier that, if we could, push a lot more funding and efforts towards use case validation and continuing to do that, you would see the maturity of the quantum ecosystem, I think, especially sensors, accelerate quite a bit. Because, unlike MEMS, which is typically like a silicon-based, etched-based process. So you're dealing with ideally maybe a single material, maybe a couple of material variations in there. Quantum is a highly complex system. You need a light source, a laser, you need some interrogation, something you're interrogating. Maybe it's molecules outside the package, or for us, it's atoms inside of the package, the atomic cell. You need a detector, and then you need all these control electronics to stabilize your light sources, to stabilize any temperature, to mitigate environmental noise that's injected into the system. And so you don't really find other product devices that are as integrated as you would find a quantum system. You're dealing with often compound semiconductors, in our case like 3-5 lasers, which they operate very different than this MEMS fabricated package that we have to pull together to house and contain the atoms. And they all have their own independent sensitivities to environment, to magnetic fields, to temperature, and you have to account for those. And so that creates an exquisite level of challenges to understand how to deploy these in different environments. And so I think being able to, not only kind of focus on those use cases, but also I think we can probably do a better job at like how we think about telemetry and how do we think about, modeling this kind of highly complex, highly integrated, systems amongst systems to be able to, I think, integrate AI in a more meaningful way. I see a lot of industries, more rapidly adopting AI for compensation tools, whether it's temp compensation or like aging compensation in their systems, because you can model these things. You can run statistical analysis, you can create digital twins, and you can also really understand how these systems perform historically over time, and then you can compensate for those to help mature its performance in different environments. And I don't really see funding from our ecosystem going to the integration of AI to advance these type of technologies. So I say that to say that there's a lot of meat on the bone to really advance some of these quantum technologies in a meaningful way.
Yeah, I couldn't agree more. I mean, in terms of the let's get these things out in the field and pick your nail. We've got these quantum hammers that we've got these incredible advancements happening in the lab. We know how to squeeze laser light and do all this crazy stuff to get the signals even cleaner and the noise even lower. So I think what no one would ever say, start a business by finding a hammer and going looking for a nail. But that's kind of what happened with LongPath, where ARPA-E just funded a really cool technology to go kind of, okay, let's take this cool hammer and see if we can develop it and make it work for oil and gas. But I have to say, I think that's where we need to go right now, because the climate problem is so immediate, and there are so many human and social problems that are so immediate, and environmental issues. I think that we need to begin to find reasons to bring these tools out of the laboratory and into the field to drive that ruggedization work, because it takes years to ruggedize these systems for field deployment and field use, and even just transporting it to your field site is an incredible amount of shock and stress on a system. And so, what we did with frequency combs, that's kind of like the first tier quantum. And so talking about the systems that are in the laboratory today, the ghost spectroscopy and so forth is very delicate, and it will take a lot of work to stabilize it. And I think the sooner we can kind of connect the real world needs with these 2 to 5 year time horizon or even 10-year time horizon tools, we will get these hungry, young, smart, brilliant engineers on these projects being like, oh, I can solve this. I can find a way to stabilize this crazy system and get the $5 million laser in the lab into the back of a truck for, $40,000 or whatever. This is doable. I just think we need to inspire great minds to get to identify the needs. And I think that's part of what this workshop is aimed at, so that we can get the hammers out in the field looking for their nails. And obviously I'm biased. ARPA-E, I think, is incredible because that's how we got out of the laboratory into the field. But I do believe as a bipartisan funding mechanism, it could not be more important in this moment than to find funding mechanisms like that will take the high risk things that industry's just not going to undertake, and because they're too crazy, they're too far out there, but they will get there eventually, and ARPA-E can help us really push them through to being in that usable state.
Thanks for that advertisement about ARPA. Appreciate that. Could you also speak about the cost aspect? Like, since you obviously went through that path from lab to commercialization, how much was the cost potentially an impediment, and how did you guys think about that?
I mean, that was really what ARPA-E was, what that funding was in part awarded to solve, was the in 2012, the dual frequency comb laser, there was maybe like 1 or 2, and the one was at NIST, and it was like a $5 million instrument of cables and fiber optic stuff, like fishing line all over the place. And ARPA-E gave that award to try to drive down the cost. And, ruggedization kind of also drives cost down, or can, finding ways to miniaturize things and so forth. So that was a big part of our journey. Oh, and the other thing I'll mention is finding the commercial drivers. I think that it's like such a privilege to be able to work on methane emissions from oil and gas, because that's also lost product. That's like spilled milk at a dairy. So we're all rowing in the same direction. But I think that there must be a million other things like this out there where there's a real commercial need for these things. And if we can find those niches to justify the funding to bring these instruments out of the lab and drive that, that'll also help with the cost out and kind of getting into that commercialization pathway.
I'll be quick, but I couldn't agree more in terms of, I think the basic technologies exist. I think the key is, funding organizations like ARPA-E or NSF or NASA, if they could tell the community saying like, we need this capability, I think we have enough workforce and capabilities and technologies today to meet that challenge. But because it is so spread thin, and they are not looking for a single solution for a single approach, it is very hard to focus. So that's why, everybody just about that I talked to in different government agencies are funding magnetometers, NB diamond magnetometers. Is that the right approach, or should ARPA-E only focusing on NB diamond, the other one does helium vector helium magnetometers, and the other does a silicon carbide? So that in a way that if the government organization kind of coordinate in a way how they want to invest in advancing a technology, you could probably get a better return than try to say, build me a magnetometer per se. Same thing applies for this workshop. If you can tell us what is a critical measurement that you need to solve your problem, we can really concentrate our resources to build up that payload to deliver that measurement. In terms of climate science, in the ocean, you have a mixed layer depth, you have an ocean altimeter, you have ocean currents, ocean vector winds, surface temperature, atmosphere and ocean mixing. There are so many variables that you need to observe. So out of all those variables, what is the most critical measurement that you need in order to reduce that uncertainty in your overall model or process models? And if you could tell us what that is, then we know how to come up with a solution that could deliver that measurement. So that's the kind of critical exchange that we need from the science community and the technology community.
And I just wanted to build on that to say, and whatever your concept of is what is the limiting precision, for example, like I do think that my understanding of these technologies is that you don't, some of those like things we always just assume we can't get a better measurement of this or that. I think that should be explored.
Thank you all. So just to wrap up this first part of the panel discussion, maybe if each of you could talk about like just personal opinion on what would be that killer app for climate and weather monitoring type of application with quantum sensing, if resources are not a constraint, maybe just a brief one-liner if each of you can share your thoughts on.
Yeah, I think I'll be biased a little bit because the fact that timing ends to be kind of like a bedrock technology for so many different applications. But I do think that the integration of these tools in autonomous systems, and kind of I touched on that at the beginning, will be a great opportunity to kind of go in parallel with the growing and emerging field. I think you're going to find so many application spaces that autonomous systems, small group 1, group 2 UAS platforms, all the way to big kind of drones are going to be deployed at scale. And we can think about the future in 5-10 years. Sensing is going to be an enormous part of that. And how do we, equip these devices, at the right price point, at the right form factor, and with the right interface to be able to get integrated into these autonomous systems? I think will be a huge opportunity to start now understanding how it can be differentiated and integrate with. So that relates to timing, that relates to magnetometers and doing any magnetic anomaly detection, that relates to any surveys and future surveys and how those continue to evolve and emerge, and other aspects as well, especially in space applications. So I think if we kind of anchor towards that, you would find that this could be a coattail to allow us to kind of grow and scale.
Caroline, maybe beyond methane sensing, like what else you think is in the horizon?
Yeah, from a climate and environment perspective, I think it's really exciting to see where I think we are poised to go with broader absorbers. I think that you had mentioned cesium earlier. And so things like that, things outside of the near infrared, which is sort of relatively easier to measure. So kind of getting into the mid infrared. But ultimately, I think continuing to drive down cost, continuing to field instruments that do make those more difficult mid-infrared or broad absorber measurements, I think will really open the door to just getting more ubiquitous, high quality measurement of atmospheric constituents. Isotopes is another one. So the quantum technology's ability to kind of drive down the SNR will allow for better measurement of isotopes, useful for so many different things in the climate environment.
So just as there is no limit in terms of resource and what we can do. So if you build a digital twin in a computer, quantum computer model, and if I were to give you one measurement, whether it's a height of the ice thickness or height of a variability on an ocean surface at some location, can computer tell me what to measure next in order to validate that change? So if you kind of entangle these sensors in space along with the computer in real time, you detect a change at a particular location and then be able to tell the sensor to observe a tertiary measurement to validate that particular change. There will be the significant improvement, in my opinion, for forecasting and prediction capabilities. So if you kind of entangle both the computers and the sensors in space together, and then as you see a change, you want to validate those change and also the sources and sinks and the impacts in a simultaneous way, an autonomous way. I think that will tremendously improve our forecasting capability.
Wonderful. So with that, we'll open the floor for audience questions, both here in person and also online. So it looks like we have our first question.
Yeah, thank you so much for having the panel here. So I would start with Caroline with your idea of a dual frequency spectrometer. Like, yeah, that's definitely like something that can be deployed as an active sensor in a satellite, but that needs a lot of R&D. So why that is important is because that we have lots of models that can do a lot of stuff in a lot of different ways. So at NCAR, we are currently doing we're implementing a stable isotope tracer in our numerical weather prediction models. So we have our models that can go as fine as 3-kilometer resolution. But when you're thinking about validating these models, so we have to know whether that model is correct or not. You need observations. So you have this platform called GNIP. So it's like Global Network for Isotopes in Precipitation. So this is the IAEA's initiative that is collecting stable isotope observation from all over the world. But that is at a monthly scale. So you cannot really compare your hourly observation against a monthly observation. You can downsample them, but you're losing your temporal resolution. And also, you don't have observations from all over the world. You have very limited number of observations, maybe like few hundred at any given time. So where like the spaceborne measurements comes very unique in this position is that because you have a large swath of coverage, and they have, even if they have some kind of spectral biases, they're normally distributed all over your scenes. So I would like, so one thing that just to bring in here is like NASA had a mission called TESS, Tropospheric Emission Spectrometer, that had your stable isotopes. So they had deuterium measurements from space, but that is discontinued, I think, since the early 2010s. And we don't have any like follow-up missions in the horizon. There are some stuff doing in the ESA, but the problem is, I mean, like we have a lot of hostility in the administration. They don't like to hear the word climate. And NCAR is at the forefront of that. So what would be like my question to the entire panel, like, yes, let's say you have a spectrometer. We have lots of like CRDS, cavity ring down spectrometers. LGR makes them. Picaro makes them. These are very well established spectrometers. Like, why not try and put them in a spaceborne like mission? I mean, like, what's the problem? Is it just the funding? Is it the R&D? Or is it the need from the audience?
I think I'm understanding. You mean like a cavity ring down? I think that as well as our dual frequency cone measurement requires a reflector or like a mirror. So the cavity ring down, I think, needs 2 mirrors. I don't know if you could do that Earth to like use the Earth as a reflector and bounce it back and forth. But I think there's some middle ground between that's needed between, a sparse network of flasks of air collected and sent to a laboratory at NOAA to be analyzed for trace gases, and a satellite observation that, although maybe the errors are normally distributed, it's still an incredibly difficult measurement to interpret, and it's a total column integration. And so I'm not arguing for like frequency combs or anything else as the middle ground, but and cavity ring down instruments are incredible because they can be in situ, so you can leave it there in the field. But maybe there's some middle ground where maybe these quantum sensors can fill that ground of a true Dreier mole fraction measurement that's maybe not too expensive and maybe does cover some larger span between the cell and the CRD instrument and the total column of the atmosphere. So yeah, and then of course just aligning it to our goals. Do we need to better pinpoint wetland methane emissions globally, or do we just need to hammer down industrial sources and understand what those are so we can reduce them? I don't know, but yeah, I mean, or do we just need to predict climate impacts on human populations? So I think that the sky's the limit. I mean, I think we are ready now for like a new type of atmospheric trace gas measurement because, yeah, we've been limited by the things that you described, but the sky's the limit. Yeah.
I mean, just to add, because the TES is a FTS instrument, it died because of the laser failure, but NASA is developing at least 3 different types of spectrometers. One for something called the HIMAP. It focuses on shortwave infrared and UV to do a lower troposphere a measurement of the ozone and other air pollutant measurements. And then we're going to have a spectrometer called the STRIDE. Goddard is going to run that mission, so to take over some of the TES and MLS measurements. So, probably within 2-3 years, you'll have a follow-on missions that's going to be filling those long-term climate records on the ozone and air pollution and aerosol measurements. So don't be despair. We'll continue to have that. But as far as the quantum sensors concerned, quantum lidars and things like that are in the concept phase, and hopefully in 10 to 15 years it will replace them. But for now, we will have a continued measurement of those.
Okay, yeah, thank you very much. My name is Junyu Liu. I'm assistant professor of computer science at the University of Pittsburgh. So I primarily have questions for Jyotsna and about ARPA-E. So primarily, my question is that firstly, about the issue between like academia and the industry, and you guys already have a lot of fantastic discussions. So I have a question about the focus of ARPA-E. Like I look at the funded grants from ARPA-E before in the QC to the Cube program, and then like there are like 9 programs in total, but 8 of them are leading by industry. And then there is only one of them is leading by academia, by Caltech. So I was wondering, like how do you think about the ARPA-E's focus in the next stage? Like we know that like nowadays, especially like commercialization is super important for pushing those technologies from lab and theory to the engineering and to the industry realizations. But on the other hand, they are, although quantum sensing is relatively mature, but especially some very crazy stuff like entanglement or like a quantum sensor integrated with quantum network and quantum computers, they are relatively at the earlier phase. So then something might still happen in academia. So what is the next focus that you would recommend us to, let's say, apply? Should we like consider more about the industry focus, or should we like more consider more fundamental research level? This is my first question. And second is about the definition of E in this ARPA-E. So because during your talk, I have an impression that you are primarily working on chemistry and material science, but actually for some of the awarded programs, it seems to be like more for general usage instead of specifically in material science or chemistry. Although like energy is like everywhere, like around the world. So I mean, but I was wondering like how broad this could happen like for the term energy. Should we specifically talk about designing a material or chemistry that is energy related, or should we consider more broader usage related to energy? And then for the remaining opportunities, like I would like to know, so what we will proceed next for the next opportunity in ARPA-E, sorry, yeah.
Sure, yeah. So if we look at ARPA-E as a whole, actually majority of the projects are led by universities. So we absolutely have nothing against academia and projects led by academia by any means. For QC Cube, this quantum computing program, it was really a matter of the quality of proposal that basically, it ended up like 7 projects being led by companies. But in most of the projects, I believe 6 to 7 out of the 9, there is a university partner, even though the prime or the PI is not the university, but they are partners. Now, in the broader sense, though, for ARPA-E, like actually our congressional mandate, like so when ARPA-E was created, we were required to look at the commercialization aspect. So it was basically we have to do that. So which is very different from NSF or other DOE agencies who don't have to look at. So they are more like basic science type of research where you show that something works in the lab, then write papers, write patents, and so on. But for us, our role is how do we now bring it to the market? And at Long Path is that great example, a success story for ARPA-E where we were able to do that. In many cases, obviously we give out the funding. These are high risk technologies, and many of them don't pan out. There are still technical challenges, commercialization challenges, but ultimately we think that there is a lot of value in academia and national labs pairing up with the industry partners, because then they bring that the practical aspects and the commercialization aspect beyond just how you can just keep improving things in the lab, because after some point maybe it's not the precision that is changing the market needs, it's something else, and understanding what is the market need becomes very, very important.
Yes.
So to your other point about the E in ARPA-E. So E, yeah, energy is very broad, and the QCQ program, we intentionally kept the application space very broad. So for instance, the examples I shared, the discovery of new catalyst materials, the specific use case there is to convert methane to methanol or convert plastics into some liquid fuels. So there is like an energy aspect because we are ultimately using them as fuels in those cases. For the superconducting materials like high temperature superconductors, obviously that can change how we are, the electricity, low loss transmission. So that is also energy relevant. So for QC cubed, that particular program, we intentionally kept it very broad, that come up with some algorithms, show that there is some application for energy because ARPA-E only funds energy relevant projects, so we have to make some connection with energy. However, as you rightly pointed out, for all the 9 projects, they have many applications beyond just the specific use case that they are targeting for the 3-year period, because we need to keep some focus, because for 3-year, if you want to get something done, if it is too broad, then nothing gets done, right? So we keep it focused for the 3 years, but beyond that, absolutely look at many applications. Now, for this potential new funding program that I described for the quantum enabled sensor networks, we are thinking of a different approach in the sense that make it more focused to subsurface monitoring. So for this one, we want to have all the projects looking at this subsurface monitoring for at least for the 3-year duration. But then beyond that, definitely we feel that these sensors, be it fiber optic sensing, gravimeters, magnetometers, whatever the sensor, I think there is a very broad application space. But for the program itself, the funding itself, we want to look at how these sensors and the sensor network can improve subsurface monitoring. So we want to focus on that aspect. And I would highly recommend that if you apply to that, it will be helpful to have industry partners or some partners who have understanding of what are the challenges for subsurface monitoring.
Right.
For example, like a well bore, it's only 7 to 8 inches in diameter. So if you want to deploy a sensor in the well bore, we don't want to block the whole well bore, especially if it is also producing oil and gas. So there are like a lot of swap, the size, weight aspects, which are also similar to like if you are putting something on the satellite. So having with academia, like say if you're a quantum sensor expert, partnering up with industry partner in oil and gas or minerals or geothermal space, I think that will make the application more attractive for ARPA-E, because then we would know that that practical aspect is also covered by your partner.
I see. Excellent. Thank you very much for your wonderful answer.
And we were only a partial award. We actually were initially not awarded for the commercialization part because we were just academia. So that's always a pathway to just say, I know this technology will support something.
Great. Thank you. My name is Gordon Zahn. I'm from Woods Hole Oceanographic Institution in Massachusetts. So I'm an oceanographer. Thank you, Wiley, for mentioning us. And so this panel is wonderful for me because I can talk to every of you about your technology I can put in the ocean. And so we are actually developing this so-called, there are several things. One example is where a colleague of mine and I, we're together leading a development of so-called self-deploying autonomous mooring system to go into ice shelf cavity at Antarctica and then deploy there for long term to measure how the ice shelf melt and then how they evolve. And because it's undersea, it's GPS denied environment we need, and also it's very accurate measurement we need. So we need to know exact time. So I'm looking at you, Wally, to look at atomic clock. We've been talking about that. So certainly I can talk to you about that. And then we also associated with that is fiber optic cable on the seafloor. Actually, just wrote a proposal last week. So I was it's great to hear your talk. So your challenges, and great. We'll be talk to you afterwards as well. And then also Jason's talk this morning about QGGPF. And I was just texting Catherine Walker, who you know, about this and potential, maybe, I don't know, that's just hand waving. Maybe you could deploy that on the mooring as well. And then another related to Carolyn, we were talking about, I also work on coral reef, mangrove environment, look at carbon flux from the ocean, look at how the blue carbon affects part of the carbon budget. And so we were just meeting last week, also talk about using laser to measure CO2 flux from the ocean. We have some idea how to do the methane, but actually your is probably more advanced than what we had. So I can talk to every of you about potential applications, but I do have questions for some of you, and it's great that Caroline already talked about reducing cost. So I would like to hear from Wally and also Jason about the cost of your systems. And also another thing is cost is power. I think now you have mentioned, and as we put stuff into the ocean, with even on the coast, a lot of times it's remote places, power is extremely limited, especially under ocean for long-term deployment. There is no solar, there's no wind. If ocean currents sometimes very weak, we actually consider that as well, but a lot of times it's not feasible. So I'm curious about all the technology you have mentioned. What is the power consumption, and what's your thinking about that? How the feasibility of deploying that in the ocean? Thank you.
Yeah, I think when we talked to Woodhull last time, I was like, the number one thing is like, what's the power? What's the power? You know, because I think the sea underwater is like the most power sensitive amongst so many different applications. And I think, you know, I'll talk a little bit about ours, but I think the overall challenge is like power is like the last thing you optimize for. Like once you get everything working, performance, target, manufacturing, then you like start to focus on power. So you guys end up kind of on the short end of the stick sometimes. So I do think that more dedicated support specifically on power would be very interesting. I think you would get a lot of power savings if there was like opportunities to integrate things like ASICs into these systems. That's like typically, you know, they think about what is the volume associated with, you know, what are the you know, like the product volume associated with any type of technology that would justify an ASIC. But then in these particular cases, I think you can get a benefit outside of cost, you know, from that. So aside that, you know, we have kind of two categories of timing solutions that we've been focused on. One is, you know, a kind of a higher performing manufacturable design, and that one sits around kind of 2 watts of power, and it allows, you know, effectively for true kind of extended operations. You know, we aim for kind of stability metrics around 10 to the minus 12, and so that typically translates in you know, various environments. If you're looking for sub-microsecond level accuracy for, you know, 3 to 4 days, but if you're looking for millisecond of accuracy, then you can really extend to those longer duration operation for months. And that's typically, I believe, where your kind of timing starts to kind of poo-poo, is when you start to go beyond, you know, a few weeks, and then you're needing to kind of maintain good time stamping. So that was an area that we found you know, an opportunity mostly in the energy grid sector to be able to kind of, you know, provide a alternative solution to some of these phasor measurement units that track current and voltage across the grid network. And as there's this kind of continued interest in getting different forms of energy and synchronizing and expanding the grid more, being able to have a broader network of nodes of timing. So that product is meant more for critical infrastructure. We're working on a second tier one, which is a lower swap one, targeting below 100 milliwatts of power consumption. That one's, I think, more attractive to the underwater space. And, you know, that one we're targeting a size of below about 5 cubic centimeters. So it's kind of relatively maybe the size of a grape. So it gives a lot more room and flexibility in these underwater applications. And in fact, the size of it would allow you to actually potentially think about integrating 2 or 3 of those miniature clocks and doing clock ensembles, because the benefit of those clock ensembles is that if there's any outlier in your clock output signals, you can kind of remove that signal, and then you can still, the weighted average of those 3 or 4, however you integrate it, ends up allowing you to have a much more extended duration operation from a perspective of your time and your precision of your clock. So I think those would be some enabling capabilities that allow you to extend those operations even further, and really get you into that kind of regime where you're able to, maintain like sub-microsecond level accuracy for weeks, if not potentially months, which doesn't really exist in that low swap category today, and we know it'd be quite interesting to maintain. So that's definitely an area of category that we are looking into. I think something that I would also say could be of consideration is the fact that in the aerial space, when it comes to drone technologies, there's this interest in like swarming, and how do we kind of improve like swarm synchronization in these GPS denied environments. And I think a lot of that technology maturity of how do you do two-way time transfer would definitely be applicable in underwater. So those are areas that if you guys have not started to explore, would be really helpful, if you're going to launch a network of 5 or 10, drones in the water, and you want to operate and kind of maintain synchronization. That kind of two-way time transfer capability not only helps on the timing side, but it improves your dead reckoning capability, to as your inertial start to drift. A lot of that time is due to the inertial performance, but sometimes that's just due to the drift in your time stamping. So those are some areas as well that I think are emerging that are very interesting to kind of collaborate on.
I think we have 3 other questions, so just in the interest of time, we can move on to the next question.
Hello, my name is Aziel. I'm a master's student at California State University of Los Angeles. I have a question for Caroline mainly, but anyone feel free to chip in. I've been doing research in molecular spectroscopy of trace greenhouse gases, and one of the big bad trace greenhouse gases at one point was CFCs. If quantum sensing can now hopefully detect more of these trace greenhouse gases, according to chemistry, we learned that CFCs were really bad. Is there potential for some of these gases, according to quantum sensing, that there could be another big bad greenhouse gas coming our way? Or better yet, if there's any data suggesting such a thing, should it exist?
I don't know. Maybe I don't know if I can answer that, but yeah, go ahead.
I mean, the quantum sensor cannot detect what the classical sensor can detect. So the only advantage you get is miniaturization and the sensitivity aspect of it, not the detection of a particular chemical species. So, using grading spectrometers or FTS type of an instrument for detecting those chemical species, you could probably miniaturize and make it more, increase the efficiency or the measurement accuracy. But just because you're using a quantum sensor, it's not something that you can detect a species that you cannot detect with the traditional spectrometers.
My name is Grace. I'm a professor from Missouri University of Science and Technology. First of all, I want to thank Dr. Sharma for moderating this session. I also want to thank all the 3 panelists for your nice remarks. And also thank you for calling for applications. And I'm offering one. So that is tornado field measurement. Actually, the 40% of insurance payout is caused by severe convective storms. It is multi-hazard atmospheric event. One of them is a tornado. So wind speed can reach 200 miles per hour, can reach 250 miles per hour. No anemometers can survive. And therefore, NOAA deployed a lot of radar, stationary radar. However, tornado path is very narrow, so it may be far away from the stationary radars. And then the researchers and NOAA develop the mobile radars, and that is the radar device on the truck. And whenever there's a tornado, potential tornadoes, they go to the field. And in order for the truck not to be damaged by hail, they need to stay far away, and also to protect the tornado chasers, and so they need to stay far away. And also the radar cannot get the information of near ground wind speed. Actually, that is somewhere we want to know wind speed and also wind pressure very much. And so I was wondering whether quantum sensing can be used to develop a quantum radar. And so this way we can, even though we stay far away from the storm, from the tornado, we can still get the wind speed very accurately. And also the regular radar that is related to the reflection, beam reflection. And then it depends on the size of the tornado warning rays, and that inference may not be that accurate. Can quantum sensing improve this observation accuracy? And also, if we want to achieve this goal in 5 years or 10 years, what things we need to do now? Thank you.
Wow, if quantum sensor can solve that problem, I think it would be great. Typically, in order to, detect, in terms of, you're forecasting tornado weather, right? You need to understand the environment first, and then based on the change, you want to be able to predict the formation of the tornado, and then you want to be able to detect in terms of path of the tornado, right? In terms of where it's going to go, and then intensity and so forth. So, typically we use radiometers, we use radars, Doppler radars, 3 different frequencies like Ka band, W band, and G band, and so forth, to fully characterize these type of phenomena. Can quantum radar solve this problem in the future? Maybe, but I think today what we need to do is to actually deploy these sensors that we currently have and try to understanding where the measurement gap is, and then try to figure out how we can deliver that measurement gap. Because we haven't even deployed the radars and radiometers and lidars all together. Try to really, assimilate those measurements into a digital twin to have a tornado forecasting capability. So once we fully integrate that aspect, and then be able to kind of have a model-driven observation strategy in terms of models going to tell you where the lack of measurements are, directing aircrafts and the radiosondes and the spacecraft to make that particular measurement. Like, I'm at the center of the a hurricane or center of a tornado. Give me a measurement 100 meters away from the center, and then does that measurement really improve my prediction capability? Next time you go around, give me 50 meters away, or give me a vertical profile of that measurement. And how those different measurements at a different given point really helps you improve your forecasting capability. So once we fully characterize that measurement strategy first, and then if there's some missing measurement gap, that's where the quantum sensor can provide. I don't think just because the new because I don't think the tornado has a quantum nature in general. So it's a classical system. It's a physical phenomena that you want to observe. So I think once we fully understand the dynamics and the interactions between the two, then we can probably come up with some approaches that can fill those gaps.
Hello, my name is Leo, and then again, thank you for the awesome discussion. So my question is just a really quick question, I guess, for all 3 of you, which is that with quantum sensing, I'm assuming that there's more sensitivity, and then my guess would be that there's a bit more data. So then I'm curious about the computing infrastructure behind, I guess, collecting the amount of data and then also transmitting it. And then at the end of the day, with the increased sensitivity, whether you guys have encountered any bottlenecks in how to process it so that it still preserves the information without overwhelming amount of data, and then I guess how you guys kind of address it, both academically and then I guess in like the commercial application. Thank you.
I'll be brief. I think something to note that with increased sensitivity, actually that impacts your noise. And so if you're, collecting a lot of data in like a 1 second period of time, for instance, then you might find you're injecting a lot more noise into your system. So, there is a kind of this cosplay here that you have to balance between improved resolution, but then your sample rate and the bandwidth that you're dealing with that system. So that's just something that you often have to experimentally kind of optimize and kind of find that bandwidth that works for your system and that sample rate. But it's not inherent that you are able to just amass a lot more data, given the same, like better resolution. It doesn't necessarily directly relate like that, but.
Yeah, I would agree. I mean, I think that you need to think about what your application is. And so these systems can probably produce as much data as you want, and you have to pick what you want out of it, and then develop the QA/QC metrics that you're going to store, and then ultimately dump the raw data. Because I mean, like for us, for example, we don't it's not actually that helpful to measure the atmosphere every, millisecond, because the turbulent dynamics of the atmosphere mean we actually want a little bit more smooth signal of methane. But there are some interesting signals within that we can develop a different metric to store that doesn't capture every single second of data. So yeah, and I think, back to this idea of like, how are you powering your system? This all goes hand in hand. So we are above ground solar power. And so we do all of our computing at the edge. And so that we're only launching, through the cell network, the basic numbers we need and the QA/QC metrics, and the drives kind of overwrite themselves on I think within a week. The raw data is kind of overwritten because it's just too much, and you got to pick what you need.
I mean, just a quick comment I heard from our quantum computing industry is that 80% of the computing resources are being used in just converting traditional computer data into a quantum computer readable format today. So if you can sense it with the quantum sensors, entangle it using a quantum network, directly feed it into a quantum computer, there's a significant efficiency by, that's one of the advantages of using quantum sensors. But like I said, that's well past the future.
And I just say briefly too, you just want to always think like it also goes into how you set up the experiment or the application space too. Because for instance, like we do some work with magnetometers where we both care about measuring the DC field, which doesn't really change for like a long period of time. So taking a lot of samples doesn't really impact it, versus you might be measuring an AC signal like a rotor on your drone, and you're trying to like filter that signal out too. And so I think it also kind of depends. You could be using the same tool, but you got to understand the application space and what you're actually trying to measure. So being able to get almost the requirements of how you want to measure something will feed into how much data that you need to pull and how much noise are you willing to accept in your data.
And you're probably going to have to go out and measure the thing first at the high resolution and collect all the data to figure out, to the point of like, we need to field these systems to learn more about what we want to learn about.
Thank you.
Hi, thank you for a good overview. My name is Priyank Dubey. I'm from Texas A&M University. So my question is primarily for Jason here. In theory, Rydberg atom can like replace multiple bands by tuning the laser and like tuning the EID transparency. But simultaneously, if we are like going to deploy it for remote sensing, then it will create more like complex decision variables. So already like this designing and planning problem for large scale constellation is gonna be a very combinatorial challenging, and still it. So if we like couple it with like laser tuning, then we couple it with signal of opportunity as you were discussing. So like, is JPL also looking into this perspective that simultaneously we are working on quantum sensing, but we are also exploring the planning like and optimization side of that idea?
Yeah, I mean, that's the part that we also need to advance in terms of using AI to sense it with a one frequency and then be able to see, hey, there's a lot of error and you need to switch over to different radar frequency to get that accuracy closed. So that's the kind of part that we're very interested in partnering with the people so that we could do direct detection and then be able to control and what signals we want to receive, to get a better measurement.
Yeah, just a follow-up question. So like you just recently told that tornado is not a quantum system, but this is actually quantum system where like quantum optimization can come and like help us, because that's something like other panelists were also talking about, formation flying swarm. So this will like create a real quantum native optimization problem. So thank you.
Yeah, I wanted to follow up on Jason's response about the tornado detection. I think you kind of hit on something there, which is a theme where this question, do we really need to develop new sensor technologies, or do we actually just need to have the will to deploy and use the technology that we actually have available? And right now it seems like we're talking quantum sensing really just means new sensor technology development. It seems to be coded here, but there are a few gap areas still. Right? We cannot observe thermodynamic state in convective systems, except for, right, DAR is getting there. Big applause to JPL for actually like looking at what else you can do with the radar, right? We do need to actually push on developing and deploying systems and capabilities that exist. We could be putting water vapor profiling LiDAR in space. Instead, we're doing a Calypso follow-on, right? So the directors of NASA and the various agencies need to actually invest in infrastructure rather than just hope that there's a new technology that's going to solve all our problems.
100% agreed. So that's where you all come in. You need to prioritize what's the most critical measurement that you need today so that NASA or anybody else can, focus their resources in advancing that capability. I mean, for natural disasters, we have hurricanes, we have tornadoes, we have wildfires, and so we cannot put resources on every single one of them. So that's why you get bits and pieces of capability advancements in these areas. So if as a nation or a science community decide, hey, tornado is my #1 priority, I'm sure we will be able to resolve it. It's just that there's just so many other things that we have to address, and that's why you only get a bits and piece of technologies on advancements in these specific areas. And it is a big problem. That's the reason why we need to have a vertically integrated structure, just like how China is doing as for the quantum development. They have a top-down requirements, and like this is what we're going to demonstrate, and then you are going to be developing this. You're going to be developing something else, and so forth, and you're going to be all working together integrated so that we can develop a capability. In the United States, that's not how we do it. We kind of let the 1,000 flowers bloom, and then try to build up the natural partnerships and collaboration to build up that capability. And both has benefits and disadvantages, and we just happen to pick one ways of advancing technologies over the other countries.
And for our funding agency, like for this potential program that I described in quantum sensing, we are not looking for like new sensor development from scratch. We do recognize that there is so much work going on in the national labs and academia, even in industries. And how can we now make it more useful, more available in the commercial space? So we want to bring them to the next level rather than building a brand new sensor. And in fact, for the program that I described, we are looking for even classical sensor and enhancement with potential quantum resources. It could be from the computing of the data side, or it could be like, enhancing with combining it with squeeze light or other examples that I share. So yeah, so our thinking is not go and build a brand new sensor from scratch. That's not our thinking at all. We think a lot of work has already been done in this area.
Okay, I have a quick comment. Rydberg sensor, we talked about, it's a multi-band sensor. Then Jyotishna mentioned about skew slide, where you can improve the SNR in some compromising. So wondering, in this field of detection, sensor development, how challenging is that to combine many different aspects of quantum so that you come up with something more optimal, improving both SNR, broadband?
So I think for us, we are thinking of working backwards from the use case. So for example, in subsurface monitoring, one of the challenges is like, as you go deeper underground, the signal, and especially if you're trying to detect it from the surface, it becomes harder and harder to detect these, say, small fractures that are underground. So for us, sensitivity is one of the main parameters of interest. And with sensitivity in mind, and and there is also a lot of environmental noise especially for like these oil and gas, geothermal operations. So the sensor has to meet those needs, so whether it's Rydberg or squeeze light enhanced sensor, I think the question is, what is the end use case that you're trying to address, and then work from there, whether, a particular sensor could meet those needs or not.
I mean, just to add what she said, you squeeze light because you don't have enough signals. For Rydberg, these active telecommunication signal, you have plenty of signal coming back. So what Rydberg gives you is a multi-frequency detection advantage. As far as the detection gains concerned, you don't need to squeeze the light in order to detect those signals. So you don't need to. But if you wanted to, you could. It's just that you get way too much signal. So you squeeze lights when you do like a LIGO type of measurement, deep dark, gravitational energy detection from the outer planet and things like that, where there's no lack of signal, then you want to use these type of scheme. For Earth observation, you have way too much signal that you can detect.
Well, I kind of disagree with that, because we are looking for about even 3 to 8 dB sensor SNR. It's huge difference in sensing atmosphere. And it's a lot of things could be done just because it's so expensive to make this high power transmitters. Sensor, but key point, in fact, we can make even, I'm sure JP are trying this one, including both active and passive sensing, the same sensor, we can do that, if provided there is enough sensitivity, which is not there at this point. And I think the impedance sensitivity is a big deal about it. And we don't have that much signal, as you pointed out, anyway.
Yeah, and signal attenuation. I mean, I agree with what you described. Like even in subsurface, when we are doing detection in well bore, there is a lot of signal attenuation, and that's why we have to drill wells very nearby if we are doing cross well monitoring. So if we can develop techniques where we don't need a lot of incoming signal, and we can enhance our ability to still detect the signal of interest from the weak overall environmental, aspect, then that will be very helpful for that application. Thank you, everyone. This was very engaging. Thanks for all the questions. And let's thank all the panelists one more time.
Climate model, which has a resolution of 50 to 150 kilometers. And this resolves much of the dynamics of the atmosphere, but many processes like cloud formation, for example, is not resolved. And of course, clouds, for example, are very important for the climate. So we need to take them into account, even though they are not directly resolved. And so the impact of these subgrid scale processes on the mean state of the system is described in a statistical manner with these so-called parametrizations. And these do not represent these processes exactly and often rely on factors that are uncertain or non-observable. So they have to be tuned, so the model has to be calibrated. Yeah, and the way these parametrizations are selected varies among the different climate models. So this also results in this large spread that I just showed. To improve these climate projections are, of course, high resolution models. So it is possible to run the climate models at a higher resolution than I just said, for example, of the order of kilometers. These then resolve various dynamical processes such as deep convection, and many biases are eliminated. But still only a part of the spectrum is resolved. And also you cannot run large ensembles of these high resolution models for climate timescales because of computational reasons. And also not all processes are resolved, even at kilometer resolution. For example, turbulence or cloud microphysics is still not resolved, and there's still a need for parametrizations. Our approach in our department is to use data-driven methods to improve subgrid scale parametrizations. So we use data from Earth observation or short high-resolution model runs, traditionally with classical machine learning, to develop hybrid models where you replace some of these parametrizations with data-driven parametrizations. This then results in better models and also improved climate projections and understanding. One example is the cloud cover. There we used 2 different sets of highly resolved simulations and extracted these input features here, then used that to train a classical machine learning based scheme to predict the cloud cover on the coarse scale, like 80 kilometers, for example. This can also be used to learn an equation classically. This can then be shown to improve the climate model. So what is shown here is the difference between the climate model output and the observations for a climate model with this ML-based parametrization for cloud cover and the climate model with the traditional parametrization for cloud cover for 3 different variables: the total cloud cover, outgoing long wave radiation, and outgoing short wave radiation. And the error gets smaller for the ML-based model. For example, here it is root mean squared error of 9.7%, and here without the ML-based 11.6%. Now, in my group, we are exploring the potential of quantum computing for climate modeling. This is motivated by the rapid progress in quantum computing and also by literature that has given hope for various advantages of quantum machine learning, such as better generalization properties, faster training, of course, with the caveat that there might be barren plateaus, and also applications for generative modeling, for which quantum computing, which is inherently stochastic, is well suited. So we applied the same approach as in classical machine learning to improve parametrizations to quantum machine learning. So the workflow is the same. We run a highly resolved climate model for a short time to generate training data. We coarse grain it to the target resolution, for example, 80 kilometer. Then we calculate the state variables and the target fluxes, for example, or cloud cover at this coarse resolution. And then in this case, now we train a hybrid QML plus ML model in this typical quantum classical feedback loop. And then in the end, we, of course, want to couple this to the climate model. So this here, it shows one time step of the climate model from t to t plus delta t. First, you run the dynamical course, so you solve the underlying partial differential equations. And then you have some of these parametrizations to represent the various subgrid scale processes, and we would replace one of these quantum machine learning based parameterization. We started also with cloud cover because it is very simple. So there we trained the QML model. We had the same inputs as for the classical case here. And then we had this quantum circuit, which encoded the input features as angles of single qubit rotations in encoding layers. Then we had variational blocks with entangling gates and trainable parameters, theta, and additional variational blocks which are repeated. And this here is also repeated to improve the expressivity of the quantum circuit. And in the end, we had a very small classical part to get from the observables here to one output, which is the cloud cover. This is all simulated quantum computing, right? It's not yet trained on a real quantum computer. And the results are shown here. So you have the altitude and the cloud cover on the x-axis, and as a function of altitude, averaged over the globe for two different quantum architectures, which we tried. In comparison with the classical neural network with the same, approximately the same number of trainable parameters, and also in comparison with the conventional parameterization as it is run in climate models. You can see here the ground truth is shown with this dashed line. So you can see here the ground truth, and both data-driven methods, the quantum and the classical, are much closer to the ground truth than the conventional parameterization. But as you can see here, the classical neural network is slightly better than the quantum neural network in this case. And here this shows the error of the predicted cloud cover, again, for these two quantum architectures and for the classical neural network. And here, again, the conventional parameterization, you can see how large the error is here compared to the data-driven methods. And we wanted to see what these quantum models learned, and we used XAI to look at that. For this, we used a method called Shapley values. These Shapley values, they quantify the influence of the input features. So if you have some model here that has input features like age, sex, I think blood pressure and BMI, then it tells you how strongly these different input features influence the output. And applied to our quantum machine learning parameterization for cloud cover, what we did is we trained 10 classical neural networks and 10 quantum neural networks with exactly the same architectures among them, and also very similar performance. So here you can see the R² values. So these are all very similar for the classical neural networks and also for the quantum neural networks. They lie between 0.89 and 0.91. And the only thing we varied is a random seed of these networks. And then we analyzed the feature importances. And here I show these SHAP values for the input specific humidity, that should be very important for cloud cover, right? Because it's one of the most important predictors of how much clouds we have in a grid cell. And you can see for the classical networks, the importance of specific humidity varied very strongly, even though all these networks have a very good performance. But some of them learned that specific humidity is not so important here. And for the quantum neural networks, this was more stable. And we also did this for all the other input features. And this was repeatable, that the feature importances are much more robust for the quantum neural networks than for the classical networks. Then what we also did is we tried to develop a more complex parameterization, because we had the hope that the quantum networks would maybe have some advantage in learning more complex dependencies. And for this, we chose cloud microphysics. And there we developed first, again, the classical machine learning-based parameterization of this cloud microphysics, which was divided into a trigger and a regression model, and worked quite well to predict the tendencies due to cloud microphysics. And we developed a fully a quantum neural network for comparison, but there we had the worst performance of the QNN model. Here you can see in purple the QNN R squared values as a function of the number of trainable parameters and the fully connected neural network in comparison. And so here we did not have any advantages. Actually, we had a worse performance of the QNNs in this case. We also looked at other parameterizations, for example, turbulent fluxes, the boundary layer height, and we are looking into convection as well. What we often saw is that the performance is slightly worse for the quantum neural networks, but the training results are more stable. This is just the R squared value for 10 QNNs trained to predict the boundary layer height in a climate model compared to a classical neural network. And you can see here the mean performance for the classical neural networks is slightly better than for the quantum networks, but the training was much more stable. So if you just select a random one of these quantum neural networks, you will get closer to the mean than if you select a random one of these classical neural networks. And now we are working on coupling these QML-based parameterizations with the Earth system model ICON. And I want to make some advertisement for the virtual poster by Hedwig Keller, which will take place on Tuesday. She will show more about these parameterizations. Okay, the next topic is working on differential equations. So as I said, one approach to improve these climate projections are high resolution models. And there, of course, it would help very much if these models were faster. So for this, we have to solve the partial differential equations, so the Navier-Stokes equations, which is quantum computing for fluid dynamics. And I will not get into this. It's a very wide field. There's many people working on it. So I will just show a teaser of some work using physics-informed neural networks. So these pins, physics-informed neural networks, they can be used to approximate the solution of these PDEs. For this, you have a combined loss, which comes from the PDE itself that you want to solve, and also from the boundary conditions and the initial conditions. So this is combined into a loss. And then you train this neural network to represent this complete system here. And this is another teaser. So there will be a talk on Tuesday at 10 a.m. by Niels Clement, who is in my group. And he is working on pins which have quantum components. And he was able to show that these quantum pins, they converge during the training, they converge faster than classical pins. This is shown here. So this shows the mean squared error during training as a function of the epochs during training. You can see this quantum pin, the error falls much faster, so it converges much faster than the classical pin in terms of epochs. But if you train the classical pin long enough, you still reach the same error in the end, right? So if you would stop it after a given number of epochs here, you would think that the quantum pin is much better, but if you then train the classical pin longer, it will also come to the same small error. And Niels will also show that the mean squared error of these quantum pins, it depends how many parameters are in the, so it's again the hybrid quantum and classical network, and you can vary, of course, how many of these parameters are in the quantum part and how many are in the classical part. And he showed that the more parameters you have in the classical part, the higher the error of the quantum pins. So I hope you will all attend his talk on Tuesday. Okay, and the last topic I wanted to show is this model tuning or calibration of climate models. For this, we used we based our work on classical machine learning again, where we developed a machine learning assisted automatic tuning framework. So this tuning, like I said in the beginning, it is finding the best set of these three parameters which come from the parameterizations in the climate model. And what you want to achieve is you want to have a small difference from observations. So you run the climate model for historical simulations where you know where you have observations and you know what should come out of the climate model. And then you choose some metrics that you want to tune for, and you identify parameters to tune. And then you can apply this iterative optimization, which is a Bayesian scheme applicable to costly black box functions. So you basically first run the climate model as given number of times to generate a perturbed parameters ensemble, PPE. Then you get these black dots here. So these are the outputs of this first PPE where you run the climate model. And then you fit an emulator to the PPE for which you use machine learning in this case. And later we will replace this step with quantum machine learning. And then you get some emulator prediction, which is shown in this dashed line here. And the emulator knows its own uncertainty. So it knows if it is far from the points of the PPE, it has a large uncertainty. It also knows that what the observations would be. So it basically says, I want to explore this region of the parameter space next, where either I have a large uncertainty or where the distance to the observations is small. So these are promising parameters to look at next. This is given by this implausibility metric here. And this then shrinks the parameter space. So you rule out some of the parameters that you were looking at, and then you reiterate. And this way you get closer and closer to the observations, much cheaper than if you would not have an emulator. If you had to run the climate model for all these steps, it would be much more expensive than using this emulator. Okay, and here we looked into using a quantum Gaussian process as a kernel in this emulator. And so this is a kernel that is evaluated from a quantum circuit, and we use Lorentz 96 as a toy model. This is well known, of course. So there you have slow processes and fast processes, which can correspond to Earth system model. And here, what we saw is if we compare 3 different quantum kernels to a simple classical kernel, we get a very good performance of these quantum kernels. So these are the R² values of these quantum Gaussian processes. And for the quantum kernels, you get a very good performance compared to this RBF simple classical kernel. And this shows how this parameter space is shrinking. So you want to go to a small, not ruled out yet, fraction of parameters. This shows this here are the quantum kernels, and this is the classical kernel. And you can see that the quantum kernels are converging nicely, but in fact, the classical kernel, you get to a smaller error in the end, but more slowly in terms of these waves. Okay, and this brings me to my summary. So I showed that climate models can be improved with classical machine learning, and there is some potential of quantum computing to boost climate modeling. And my point is that it is important for the climate modeling community to position itself to take advantage of this rapid quantum computing progress, and also to advocate for quantum computing developments with applications in mind already, so that we can advance hardware, software, and application co-design. Thanks for your attention. Any questions?
Thanks very much for that excellent talk, Dr. Schwabe. It was really great. We have a couple of minutes for questions.
Thank you for the great talk. So you mentioned that some of the parameterization comparison for microphysics, I don't think you have results. So how does that compare for precipitation, for example, in the QPN?
So for the microphysics parameterization, we had for all the tendencies, we had the better performance for the classical network than for classical machine learning based parameterization than the QML parameterization. All tendencies.
So I was wondering about the extreme part of the precipitation. So does that because we know that in literature, there is a tendency for machine learning based emulators to smooth out the extreme part of the precipitation distribution. Do you see the same kind of behavior for the QPN?
We have not tested this in detail, so we have not coupled it to the climate model yet. So we have only looked at the tendencies themselves, but it would be interesting, of course, to see if we couple it to the climate model, if the climate model then results in better extreme events. That would be very nice, but we haven't tested it yet. Yeah.
So we have a few online questions. So let's go with Johannes.
Hey, thank you so much for the great talk. I have a comment and a question, if you don't mind. So comment-wise, maybe I missed the session title wrong, but is it surprising you're talking about basically quantum PDEs or Navier-Stokes? They were talking about pins and not about there is quantum solvers. Now, and I think that's maybe a key question, why to go to the pin. But actually, let me go with my actual question then. Maybe it's two questions. The thing is, you're simulating basically most of these things. Now, the parameterizations are simulated. And isn't the key point that you want to estimate if you get any benefits if you go to actual hardware now? So the assumption is with quantum ML, if you go to actual quantum hardware, you would have a much bigger latent space. You try to estimate if you see a scaling behavior, if you scale the latent dimension, no? Did you ever look? Does that make sense what I'm trying to say? If you do the quantum ML at low latent dimension, you're just basically having a funny conventional AI system.
Yeah, I mean, we are just starting to look into running it on real hardware, and we cannot train on real hardware yet because it is too slow. So we have run inference on real hardware, but of course it's noisy. So I think there's still some.
But do you see scaling laws already? When you send even on the simulation. So for example, that's what I said, if you scale up the latent dimension and you see sort of you see a scaling like a power law behavior or something, no? Then you would say, oh, we assume if you make this larger, we would be over there, that sort of something.
Yeah, we did for the microphysics parameterization, we did look into the scaling with a number of free parameters, right? And still the classical was better. But yeah, I think we should investigate this further for sure, because we still haven't explored all the potential of quantum computing. So yeah, thanks for the comment.
Thank you so much.
We have a few online questions, but for the sake of time, let's do one more. So we have one from Bjorn.
Hi, everybody. This is Bjorn Lütjens from IBM Research. Great talk. Thank you so much. I was wondering, in your slides, I understood that in many of the cases, the quantum machine learning approach or the quantum Gaussian process can improve over the classical ones. I was curious if you can elaborate on what the key fundamental properties are that you exploit from the quantum processes. I think, for example, on slide 27, you were mentioning that the kernel can achieve a better R2 than the classical kernel, and I was curious why that is the case.
Yeah, I mean, I have to say, I said then a simple classical kernel, right? So we have not looked into all the different kernels that you could use for a classical, and we are not sure why yet. So what we see often or consistently is a faster convergence, right? You could also see this, that the wave, with the waves, it was the not ruled out yet space was shrinking much faster for the quantum kernels. But whether this is some property of entanglement or of whatever, we can only speculate. So I cannot really say.
Yeah. Got it. Thank you.
Thank you again, Dr. Schwabe. Our next speaker will be Dr. Junyu Liu, who's a professor at the Department of Computer Science at the University of Pittsburgh. Dr. Liu's work bridges quantum physics and modern computer science, focusing on developing practical real-world applications for quantum algorithms, networks, and quantum sensing technologies. Thank you.
Yeah, thank you very much. And it's a great pleasure for me to be here. And I feel the workshop is fantastic. And thank you very much for your introduction. My name is Junyu Liu. I'm currently an assistant professor of computer science at the University of Pittsburgh. So the title of my talk is called From Near Term to Fault Tolerance, When Quantum Machine Learning Can Outperform Classical Counterparts in Earth Observation. So my primary interests, trained from a quantum information science background, was trying to find useful real-world applications in quantum technologies. That is primarily related to quantum computing and quantum sensing.
So especially recently, we formulated a team, and together with two of my graduate students, and also Dr. Yichun Xie from University of Maryland and Dr. Xiaowei Jia from Pittsburgh as well, who are expert in earth science. So we are forming a team together on trying to find if quantum machine learning or quantum technologies in general can be helpful for some geoscience or earth science related problems. So, and then we try to do some very early investigation in the subject. It's very novel. So not that many existing work in this interdisciplinary subject. So we are trying to make some connection between those fields. So I feel that the workshop is very excellent for me. So as a brief introduction, there are lots of definition of quantum machine learning, but in many situations, quantum machine learning in the near term means a trainable hybrid quantum circuit, where you are going to make those quantum circuits that is inside a classical loop, and then you try to update your, you can encode your data into a quantum circuit. You can also put your parameter in data in your quantum circuit, and then you can try to train some parameters based on the measurement results, and then trying to update those parameters by quantum control, and those parameters can be classical. So basically, this is a central idea of so-called variational quantum algorithm that we have explored in so-called noisy intermediate scale quantum, or NISQ era. Although that it's very challenging in the situation to prove a quantum advantage, but my personal view is that I think this is the best way where people from outside quantum could try to approach some quantum algorithms and trying to make connection between quantum information science and the real world. So, however, we cannot always stay in the current noisy stage. So currently we are in a stage, according to John Briscoe from Caltech, they call it the NISQ, where NISQ stands for noisy intermediate scale quantum, which means that we are able to control 50 to 100 or even to 1000 qubits, but it's very noisy. So the error rate will be maybe around 10 to the minus 4 per gate. So then basically that means that you can only run in maximally 1000 qubits, but only with 1000 quantum gates. Those quantum gates, they means that some logical basic operations and also some rotation gate. And of course, for any large scale algorithm, it should be far from that number of gates. So then that means that if we are limited in this NISQ space, we cannot have that many applications, although people are trying to work very hard on finding useful algorithms. But however, so nowadays we are approaching another era, which is the era of fault tolerance. There are lots of companies trying to correct those errors and then trying to make your quantum devices to be larger and larger with much less error rate. So the technology is still developing. We already say that lots of startups and industry leaders who already jump into the subject. But however, a large scale fault tolerant quantum computer is not there yet. So before it happens, it might be some years of journey to really invent a commercially viable fault tolerant quantum computer. But however, so before that, maybe we can already try to do some useful things, and from near term to fault tolerance. This is a perspective of the talk that I will give today, which is trying to deliver the knowledge where maybe during the quantum hardware is improving, we will gradually get some benefit from quantum devices for earth science or weather or climate related applications. So the first trial that we did in our work, which is called quantum vision transformer. So this is a architecture that has been designed by a few years ago. That basically the idea is that you take a traditional vision transformer and then you try to replace neural networks from classical to quantum. And then, so there has been end-to-end pipeline have been invented. And then there are empirical evidence that shows that those kind of models that actually has a pretty good scaling law, which means that comparing to potential quantum advantage we usually seek on, say, scale of the computation, the advantage potentially quantum vision transformer can deliver might be related to the generalization capability, which means that basically it can achieve the same performance, but potentially using less and less training parameters comparing to classical counterparts. So we try to use this model to some earth science related problem. And then we find that for the float detection related applications, it actually has a higher score comparing to some other well-known float mapping related problem in remote sensing. And moreover, we try to investigate some other data sets from with earth science related to satellite data, which usually has a spectrum related structure. And then in this situation, what we did is based on the quantum vision transformer approach. So what we did is that we tried to redo tokenization by redo vectorization, that we embed those original geoscience related data into different groups of tokens. So for those kind of methods, we call it quantum spectral kernel attention. So this is the novel designs that is actually specifically for quantum application of earth science. And using this method, we find that originally the earlier vision transformer may not be able to comparable to classical counterparts, but after this design, actually it can work better and has potentially better scores and with maybe potentially less or comparable training parameters. So then there are some ongoing work related to that, which is that maybe use some earth science or geoscience native methods, and we can actually improve the existing architecture. And also, to move it towards early fault tolerance, where this model will be stronger, we are recently trying to adapt some novel partial quantum error correction ideas by trying to only correct the errors from CLIVAR circuits instead of the continuous rotation circuit, which is a single picobit but has relatively less error. We are able to try to achieve partial quantum error correction. And from there, we are trying to explore for some earth science related applications, can partial error correction be better than the original NISQ algorithm? So this is also another work in preparation that we are trying to improve our model from near term to fault tolerance. That's what happens in the middle. Moreover, in the fault tolerant quantum computing regime, so there is a recent important paper or important theorem about there are potential exponential quantum advantage for future fault tolerant quantum computers on processing massive classical data. So it's well known that there are lots of claims for fault tolerant quantum computers that potentially can have advantage in machine learning. But usually they are suffering from the encoding problem, where how you are going to move classical data towards a quantum world without introducing additional too much overhead. And then actually those theory problems have been clarified a lot in thanks to some very smart theorists, such that you can actually try to design some smart oracles that in order to load classical data efficiently. And then, so this new method and associated with some other data structures, this new method is called quantum oracle sketching, and combined and compared with the previous designs like quantum random access memory, people can show that this can leverage for fault tolerant quantum computers, it can leverage potentially exponential quantum advantage, at least in theory. So there are some existing already some benchmarks for various different data, like for instance, like a movie or some RNA related studies. And then, so recently we are trying to benchmark this particular model in some earth science related applications. Like primarily we are interested in binary classification type kind of problems in various different geoscience applications. And what we find is that it's indeed some exponential advantage could happen in the sense that you could use much less amount of quantum devices to process a large, gigantic amount of classical data. So this is something that we are trying to point out in the fault tolerant era. So it's theoretically grounded that quantum devices can provide some help for some earth science related problems. So as a conclusion, so actually this is a short talk in principle, only 15 minutes. So I have to conclude it very quickly that I think overall for the earth science, including geoscience or weather or climate change related science. And actually, it may get benefit at every stage of the hardware transition of quantum computing, from near-term to early fault tolerant to eventual fault tolerance. And then, as long as the hardware is improving, I will be very excited to see more and more potential applications from quantum information science community towards the real-world application. So that is the end of our talk, and thank you very much.
Thank you. Thank you, Dr. Liu. Our next speaker is Lucas Chan from Brown University. Lucas focuses on applying quantum computation to complex nonlinear dynamical systems. Today's talk will be on quantum computing for the climate.
Thank you for the introduction. Hello, once again, I'm Lucas Chan, and I'm here representing Brown University to present our work on using noisy intermediate scale quantum hardware to calculate the statistics of nonlinear dynamical systems. I will begin by describing our formulation of these dynamical systems. Consider here the Langevin equation, where u of x is the velocity function and eta is some additive stochastic forcing. The Langevin equation describes the equations of motion of our dynamical systems. And the key idea here is that these equations of motion are in general nonlinear ODEs. And since quantum mechanics is linear, we want to transform these nonlinear ODEs into linear PDEs. Then we would like to take advantage of the fact that quantum computers have exponentially large Hilbert spaces to help out with the increased dimension that may come from this transformation. With that being said, I will now describe our methodology. I will begin by introducing the Fokker-Planck equation. The Fokker-Planck equation is a linear PDE that describes the flow of the probability density function of a trajectory. And importantly, the Fokker-Planck equation respects the conservation of probability. And we can see this through the flux form of the FPE. This first equation that we see here is the Fokker-Planck equation. It is a linear PDE once again, and we call this LFPE term the linear Fokker-Planck equation operator, or simply the FPE operator. And the second equation here is the flux form of the FPE, and from this we can see that it indeed respects the conservation of probability. One important aspect of the FPE is that its statistical steady state is its ground state eigenvector, or what we call the zero mode. Some work done by Dr. Alawala and Professor Marston. This work compares the PDFs of the Lorentz attractor. The top is the PDF recovered by accumulation or direct numerical simulation. And the bottom is the PDF as recovered using the FPE method. And we can see that there is a strong match between the two. For our purposes, we do not focus on the Lorentz attractor. Instead, we focus on the one-dimensional nonlinear Ornstein-Uhlenbeck problem, which is an easier problem. The velocity function is given by this u of x up here, and we can see that indeed it is nonlinear. The nonlinear Ornstein-Uhlenbeck problem describes the trajectory of a particle in one-dimensional space. And an important property about this problem is that there exists an exact analytical solution to the Fokker-Planck equation, as we can see here using this second equation. I will speak a little bit on the parameters of this problem. We fix B to be positive for stability purposes, but interestingly, if we fix A to be negative, the particle is forced away from its central point. It's forced away from zero. So we instead see this double peak behavior here on the right. Gamma here is simply the covariance of the stochastic forcing we were talking about earlier. To be able to use quantum computers in this case, we first need to project the FPE, the problem, into a finite basis. And to do this, we use the Hermite polynomial basis, whose basis states n are given by this third equation here, where capital H sub n is the nth order Hermite polynomial, and L is the user-defined length scale. You can see here that we used a length scale of 1, and this actually is a suboptimal choice for the length scale, which helps us illustrate nicely how the basis converges to the exact analytical solution. And on the right, we can see here that it takes about 64 basis states for the PDF in the truncated basis to converge to the exact analytical solution. Now, we can find the elements of the FPE operator in this basis using this fourth equation here. And we, in fact, fix the Hamiltonian that we input into our quantum computer to be Hermitian. And we do this by taking the adjoint of the FPE operator and multiplying it by the FPE operator itself. And the reason we do this is so that we can use algorithms that were built for Hermitian matrices. Now, the reason this transformation is valid for our purposes is because the ground state eigenvector of this Hermitian operator is the same as the ground state eigenvector of the FPE operator itself. In order to be able to use our quantum algorithms, we must map our problem onto the computer itself. And the first thing we need to do is put the FPE operator in a form such that it enables this mapping. And the idea here is to represent the FPE operator using ladder operators from the quantum harmonic oscillator to enable this mapping. So we see the ladder operators here. These are our familiar ladder operators from the quantum harmonic oscillator. And doing some simple algebra, we can get x and the partial differential with respect to x in terms of these ladder operators. We can then substitute this x and partial differential with respect to x into the FPE operator to get this representation of the FPE operator using the ladder operators from the harmonic oscillator. Then the last step we need to take is to map the polynomial basis itself to the qubit basis. And this consists of two steps. The first step is mapping the basis states themselves, and then the second step is mapping the ladder operators. Now, the mapping of the Hermite basis to the qubit basis is quite easy. All we need to do to complete this mapping is to find the bit string representation of the Hermite bases. And these bit string representations make up the qubit basis. The ladder operators are a bit more difficult. On the left, we have our very familiar lowering operator in the Hermite basis. And for the purpose of this presentation, we will use an example to show how we construct the ladder operator in the qubit basis, and we'll let n equals 4 for illustration. So again, on the left, we have the lowering operator working in the Hermite basis. It's very familiar for us. But on the right, we have the lowering operator working in the qubit basis. And importantly here, we have unique, what we call state-wise lowering operators for each possible state that the lowering operator could work on. So for example, we have this unique 3 to 2 state, and then this unique 2 to 1 state, and then this unique 1 to 0 operator. And we borrow ideas from the Jordan-Wingard transformation to create these operators. As you can see, we have these linear combinations of the Pauli matrices. And in particular, to keep a qubit in the same state, we use a linear combination of the I and Z matrices. And to flip the qubit, we use a linear combination of the X and Y matrices. Now, once we have defined all of these state-wise lowering operators, we can then sum them up. And this sum is the overall qubit lowering operator. And of course, the raising operator is just the adjoint of this lowering operator here. And as I said before, this example was in n equals 4, but this qubit ladder operator can be generalized to an arbitrary n following the same pattern. Now that we've covered the mapping of our problem to our qubit basis, we can now cover the algorithms that we use. The first algorithm that we use is the variational quantum eigensolver. This is a hybrid quantum and classical process that aims to solve for the ground state eigenvalue of the inputted Hamiltonian. And the process works like this. The user will input an ansatz or trial wave function into the quantum processor. The quantum processor will then calculate the expectation value of the inputted Hamiltonian, and it will then pass the expectation value into the classical processor, which then optimizes this cost function using some user-selected classical optimizer, and then it will update the parameters of the ansatz. Then what will happen is the classical processor will pass these parameters back into the quantum processor to restart this optimization loop. And this loop is repeated until convergence or until a maximum number of iterations has been reached. Now, traditionally, this algorithm has been used to find the ground state eigenvalue. However, we already know that the target eigenvalue is 0, and we are more interested in eigenvectors, specifically the ground state eigenvector. So we instead use the VQE to prepare this ansatz such that it is a close approximation to our ground state eigenvector, and then we will use another algorithm to actually recover the ground state. So this algorithm is called the QSCI method, or some may know it as the SQD, the sample-based quantum diagonalization method. It is another hybrid quantum and classical process, and it begins by us inputting the state that we recovered from VQE, though it could be, this input state could be recovered from any general quantum algorithm, but for our purposes, we use VQE. The state is then passed into this quantum processor, and the quantum processor samples the state an n number of times. In other words, it measures the state for an n number of shots, and then we select the R most frequent configurations to create this subspace capital C sub R. What I mean by R most frequent configurations is just the basis states that show up the most amount of times when we've done our measurements. And these configurations are the basis states that provide the most support to the ground state eigenvector. We then pass this subspace into the classical processor, which then projects the Hamiltonian into this subspace and diagonalizes in this subspace. And finally, the output ground state is given by this equation here, where lowercase c sub x is just the xth element of the ground state eigenvector as found in the subspace. Now, we do recognize here that we still use classical processing to project and diagonalize the Hamiltonian, but the aim of the QSTI or the SQD is that we project the Hamiltonian into a subspace that is small enough, helps this diagonalization to be fast and feasible on a classical processor. So we report the results of the VQE here, and almost remarkably, we can see that the VQE and QSTI method returns results that are exactly match the classical numerical diagonalization in both the noisy simulation and on the hardware, on the real hardware. On the left, you can see that we did indeed reach our target basis state count of 64 basis states. We ran this simulations on the Nairobi simulator from IBM and using SPSA for 300 iterations. On the right, we can see that we also, again, the VQE and QSTI method returned results that matched with the classical numerical diagonalization. We ran these on IBM's real Marrakesh device, and we used Kobe law for 18 iterations. Importantly here, on the hardware experiment, we used only n equals 8 basis states. We were tight on QPU time and wanted to make sure that we could get results while still running on hardware. Really quickly before I go, I guess the arrows didn't show up here, but really quickly before I conclude, I would like to cover our work that we've done with the ADAPT VQE. The ADAPT VQE is a modification to the VQE that attempts to circumvent the barren plateau or vanishing gradients problem by iteratively creating an ansatz that is educated using the excitation operators. And the algorithm is as follows. We define an excitation operator pool and also initialize an ansatz. So this would be through methods such as random initialization or Hartree-Fock. So markedly different from the hardware efficient ansatz from the regular VQE. Then we go into this central loop here. The hours are supposed to go this way and then come back this way. But essentially, we calculate the gradient for each excitation operator in the pool, then evolve the ansatz using the operator with the largest gradient. Then this evolved ansatz is passed into the quantum processor where the VQE subprocess is completed. And then this ansatz is passed back to step 3, where then the loop is repeated. And this loop is repeated until convergence. Now, interestingly, we saw that this is results that we got from simulation. Interestingly, we see that the ADAPT VQE actually has much more variance in results from simulation to simulation, unlike VQE, which is very unexpected. We would expect that the ADAPT VQE would perform better, or at least match the performance of the VQE. But this suggests perhaps that the ADAPT VQE for this problem is not the optimal choice of algorithm. But it perhaps might come in handy in the future for problems that are more complicated or have more parameters that run a higher risk of running into the barren plateau problem. So we have seen that the VQE can work well for this one-dimensional nonlinear Ornstein-Uhlenbeck problem. But of course, the key question that we would like to answer is, can quantum computers offer an advantage over classical computers in finding the statistics of high-dimensional dynamical systems, such as the fluid Earth system? And perhaps this question may not be answered until we reach a later stage in the quantum hardware. But the next steps for us is to further investigate the efficacy of VQE on modern NISQ hardware. As I stated before, we were tight on QPU time. We would like to be able to run for a longer time on NISQ hardware to really test the robustness of VQE and importantly, increase the number of basis states that we used. We would also like to investigate the extent of the dimensionality reduction of QSEI, since its speed up hinges on the fact that we are reducing this dimension. We would like to see the magnitude to which we can reduce the dimension. And finally, for the long term, we asked some questions. Can a quantum algorithm be developed such that it can recover eigenvectors without the need for classical diagonalization like the QSCI does? Or are there other approaches that don't require diagonalization? There has been some work done to address this second question. For example, this paper by Bravi et al. On the archive titled Quantum Algorithms for Stochastic Nonlinear Differential Equations. And it discusses methods to map observables of nonlinear dynamical systems to a quantum computer using the Hermite polynomial basis. And then it simulates time evolution on a quantum computer to recover the expected values of the observables. So while the difference between this method and ours is we focus on wave functions, this method focuses on observables. I think that's my time. Thank you very much.
Thank you, Lucas. Our next speaker will be Shan Zeng.
My name is Shan Zeng, and I'm an independent researcher. Today, my topic is using a quantum lattice model to simulate the polarized radiation transfer. Radiation transfer simulation is very important because it's one of the core components of the climate. And second, it helps for designing remote sensing instruments and performing the retrievers. Classical simulations involves absorptions, emissions, scattering, which include the single or multiple scattering, namely the polarizations. And our quantum simulations also include the four physics. Classical simulations use many nested loops over, for example, over scattering angles, spatial grid, spectral grid. So this make it hard to speed up with the GPUs. And quantum computing opens a new path to accelerate this. Our quantum simulation include the four physics, include a Rayleigh scattering, four stalk vector, and 2D spatial grid and 3D angular grid. And this algorithm will be validated by comparison with a classical simulation of the same setup. Classical approach, the radiation transfer simulate equations have 5 terms. The left represent the time rate of changes of the radiation. And the second represent the spatial transport. And on the right side gives the source of the changes, including the absorptions, scatterings, emission. And in quantum approach, we actually map every photon transport configuration to a quantum computation basis state. And each step of the state is indexed by the spatial index XY and incoming and outgoing direction D in and D out. And the source and the live stream index SL and stock vector state ST. So by applying the emission, scattering, absorption, and the propagation gate to the initial state, that gives us the output state. But because the different operators are not unitary, so we delayed them using ancilla qubit. So the final measurement is post-selected on the ancilla being in the cat 0. And so the full simulation therefore follows this process. We first of all mapping and encoding the data using amplitude encoding, and then we have to construct a unitary for each of the operators, and then we measure all the qubits and post-select on the ancilla in cat 0, and then decode the result probability back into the classical value. The model we use is a 2D and 9 velocity lattice model showing here. The first gate we have to design is the emission absorption gate. The emission absorption gate transfer the external source emission, which is J here, into the live radiation stream. In other words, J needs to be added to the S on the live stream register, while the emission itself will stay in this register unchanged. So this can be realized by applying this matrix. But this matrix is not unitary, but any matrix can be decomposed into the linear combination of poly operator. So as shown here, we can decompose it to the IX and the ZX gates. For this decomposition, we need 2 ancilla qubits to help. So to realize this, we first apply for the Hadamard gate. So which prepare the 2 ancilla qubits in an equal superposition with ket 0, 0, 1, 1, 1, 0, and 0, 1. For the I terms, it does not require to selecting any particular branch, but for the X and the ZX, we need to do this. So we apply the X gate to the ancilla 0, so flip the qubit, and we apply for the X, so we choose the X only fires when it's a ket 1, 1, and then we flip it back to 0, and we apply the ZX gate, so that the ZX gate fires in the ket 0, 1. And then after, or we apply another Hadamard gate that we combine the 4 branches, and so that's give the sum of this operator. Later, we are going to apply the absorption extinction gate. The absorption gate actually remove the part of the radiation from the live stream by a factor of A sub the absorption, which equal to the E of the K sub absorption times delta T. But multiplied by the absorption coefficient is non-unitary. So because it is reduce the amplitude of live state. To implement in the quantum circuit, we need to use unitary dilations to embed this coefficient in a larger matrix that fit into the position of 1, 1. So when the ancilla, we use 1 ancilla, that's a rotation rotation gate, RY gate. So when we measure the 0 gate, we get actually the absorptions. That's what we want. So we notice that here there's the X gate because we have to select that we applied only on this live stream gate. Then we have to, when we apply this gate, we have to switch this register back to 0 ket 0. The third gate we are going to apply is a scattering gate. That's more complicated because it's including a survival and the redistribution of the radiation. So it's very complicated. So we first look at it these terms, which is the redistribution terms. We first focus on one single scattering, income and outcome scattering directions. And so these terms, in classical way, it applies first the rotation from the rotation from the incident plan to the scattering plan, and then apply for a phase function, and then applies another rotation from the scattering plan to the out directions. But this again, all this matrix is not unitary. So we have to find we still need to do the dilations. So the same way use our RY gate to do the dilations. And then after it's become unitary, we have to look for the rotation. The rotation matrix can be applied by the RXX plus the YY gate. So now we have realized for one direction the scattering. But scattering is not just the one direction. So there are multiple directions, multiple income and outcome directions. So we need to summarize all the directions, how we're going to do this. We use the prepare and select and prepare to do it, these constructions. Actually, it's a linear combination of unitary block encoding. So prepare actually is using a RY gate to superposition, to do the superposition weighted by the angular quadrature coefficient, which is implemented with the RY rotation. And then we selected the directions and apply the unitary we have been done for one directions, and then we have to apply again this Y rotation, but towards because we have to release this ancilla toward this ancilla towards the original zero cat zero. So we have to apply the Ry minus theta angle. And after that, we have done this part. Then we have to see the whole scattering part. The whole scattering part is surviving and redistribution part. The same way, we are going to using the LCU method, that's using the Ry rotation to prepare this the superposition of the two branches, the surviving and the redistribution branch. The last operator is the propagation gate. It uses the ripple carry cascade of multiple control X gate to map the lattice index I to the I plus or I minus 1. Carry information propagate through the cascade, allowing the index register to be incremented or decremented while preserving the reversibility. If the boundary, there's a boundary layer here. If it is absorbing bound, we will add an escape flag qubit. We will set it to 0 to cat 1 if the photon has reached the boundary. And these branches are then discarded by the post-selecting the escape register on the cat 0. So now the code is completed. And we first benchmark the classical and quantum implementation on quantum simulator using both one-dimensional and two-dimensional model. This is propagation to the right, propagation to the left. We see that for different color here is for different 1D, 2D quantum classical simulation. We can see that they are overlaid very well. So the difference is actually between the quantum and the classical is on the order of 10 to the minus 12. And between the 1D and 2D is 10 to the minus 15. And these are the level of numerical precision, so can be considered negligible. So next we are showing the two-dimensional distribution of intensity and the degree of polarizations. The quantum and the classical result are quite similar. And their differences are again on the order of 10 to the minus 12. The intensity are stronger at the source because the center is the source, and decrease to the edge. And also depolarization, that's close to 0 at the center and increase to the distance. This is because this is agree with the physics because multiple scattering dominated at the larger distance. So for different time steps, for time equal to 1, 8, 16, and 16 and 32, the result again agree very well. And the differences are on the order of 10 to the minus 12. And also we look at the ratio of quantum, and this is a quantum divided as the classical for the I, for the Q, the Stoker vector Q, and the degree of polarization. So we can see that the ratio is stay around 1 very constantly. So this means that the error between the classical and quantum do not accumulate over time on the simulator, and that the quantum implementations remain stable as the simulation is extended. We also tested a range of angles that covering different azimuths and zenith combinations. Again, the classical and quantum result differs by only 10 to the minus 14 to 10 to the minus 12. So the agreement on angular distribution also is consistent. We have demonstrated a quantum radiation transfer code suited for the real applications. We have benchmarked the two-dimensional polarized radiation transfer. Future direction can include adding absorption into the radiation transfer, cloud aerosol scattering, or extend it to the 3D dimension, and run on quantum hardware. For hardware, the circuit optimization probably become very important. For example, probably a quantum Fourier transfer based transfer step in place of the ripple carry cascade. Our current implementation is fully quantum, but some component may be more efficient with the hybrid approach. So identify which part gives the best returns on the investment is an open question. Thank you.
We'll start the half-an-hour discussion session. We'll start with questions for any of the speakers. So I would like to invite both our in-person speakers on stage. So Dr. Liu and Lucas Chan, if you can join me on stage. We can start with questions. Maybe we'll start from there.
Fillmore and Carr, a question on the ladder operator construction for the Fokker-Planck equation. I'm just curious, the size of the Hamiltonian, number of qubits used to encode it, and if I understood correctly, you're finding the ground state of the Hamiltonian that coincides with stationary state and potential for extending the method beyond stationary state, I guess.
I see. So I guess so what you're asking is finding states that are not just the ground state eigenvector. That's a good question. I don't think we've necessarily looked at that yet. I think one thing that I can see as a potential issue is that I'm not sure if the ground state eigenvector of the Hermitian operator matches the non-ground state eigenvectors of the FP operator. For that, we would probably have to find another algorithm to use, or perhaps look at VQD, I think, for if we stay the course of variational quantum algorithms to use, since VQD, I think, can target states that are higher than the ground state eigenvector. It's a good question, and we can certainly look into it.
Thank you.
Thank you. So I have a question for the third speaker about the radiative transfer. So did you get a chance to compare your results with some of the available RTMs like CRTM or RDTOF? How different or similar the results are?
Sorry, can you repeat that question again?
Yeah, sure. So there are some radiative transfer models like CRTM or RDTOF that are available in the data assimilation systems for different parts of the modeling framework. So did you have like chance to compare your quantum-based radiative transfer model, and how does that compare with those kind of radiative transfer models?
Actually, no. Yes, I think I should compare to different kind of, because for the partial differential equations, they are always different. Even in the classical simulation has different way to simulate it. So my way is the lattice model, because for me it's more easy to do. They have different ways, like Monte Carlos. They have the quantum Fourier transfer. Those are all very good, but I think that I will next try is the quantum Fourier transfer, because I think maybe, okay, so I look at a paper that says that by this method, because it will it can chunk the frequency, so it don't need too much probably don't need too much qubit, and also probably can help for the noisy hardwares that probably do better. So yes, you're right. It needs to compare different models.
Yeah. Okay. Thank you.
Let's do an online question.
Yeah.
Hi. So I have a question for the quantum algorithm for nonlinear differential equations. So there you mentioned that you are using the VQE, right, as a quantum solver. Maybe I'm wrong, but I know that VQE cannot really prove any kinds of quantum advantage in terms of scaling, right? The problem that we have in the fluid dynamics of particle field interaction in the atmosphere is that we have a really high Reynolds number with a numerous number of particles. So basically what we really need for realistic applications, that we need some kinds of like a scaling law to guarantee there is a polynomial exponential advantage. So I wonder, because part of your talk, you transformed nonlinear equations into, I guess, a linear set of equations through the Fokker-Planck equation, like what Ravi and his team did. And then from there, can you apply those like for the current quantum algorithm to get some kinds of like a potential quantum advantage?
Yeah, that's a great question. I think something that we definitely came across was that the variational quantum eigensolver is not, like you said, will not actually prove that there is a quantum advantage here. I think I think there must be some more either research on the algorithmic side and also on the hardware side for us to be able to prove this. One silver lining I do think I see is that we don't rely necessarily on the VQE to get our ground state eigenvector. Any quantum algorithm that we can use to approximate the ground state eigenvector, we can then feed to the QSCI and recover it from there. So this is more, I guess, of a proof of concept. And hopefully as algorithms develop, we can find something that may actually give us an advantage.
Right. So one more question regarding this. So what's the difference between your current linearization procedure, which means mapping from the nonlinear classical equations to Fock-Planck equation, compared to Bravi's group's work just you showed in the last slide?
That is a good question. I think the biggest difference I see is that we're more focused on the eigenvectors, whereas they map the observables using the Hermite polynomial basis. So the methodology is different because they're mapping the observables onto the quantum computer and not necessarily the eigenvectors.
Right. So in your work, you can you deal with arbitrary nonlinearity?
Oh, I see what you're saying. Yes. In the paper that I mentioned, they don't. One of the things that they don't do is they don't require the operator to be Hermitian. So they embed the observables into a larger space that is Hermitian, but they don't require that. So they just map the observables directly.
Oh, right. Thanks. So, but in your work, can you deal with arbitrary nonlinear equations? But
oh, I see. Okay. I'm assuming that you're talking about our. So first of all, taking the FPE of the nonlinear dynamics and then mapping it to the computer. Yeah. The FPE works in general for nonlinear dynamical systems. The FPE exists for the trajectories, but the mapping to the quantum computer will be different for the different FPE operators.
Yeah, of course. Yeah. Thanks.
Great. Okay, so we'll come back to the room for more questions. So.
Oh, I'm Shan Zeng. So I have questions to Lucas. Yeah. So it's about the Fokker-Planck. So I'm aware of when you simulate on quantum computer, Fokker-Planck might already be encoded in L1 normalization. So I'm not sure how you change it to L2 normalization, but because it's more natural to, as a states normalized in L2 for quantum computer, right?
Sorry, can you say it one more time?
So I'm saying the probability density is L1 normalized for Fokker-Planck, right? So how do you change it to L2 normalization? Because when you run on quantum machines, it's always normalized in L2.
That's a good question. I don't know if I know the answer to that question. I'm sorry. But what I can say is that when we go from when we map the Fokker-Planck equation to the qubit basis, we map to the computational basis. And then when we come back, when we measure the states, we then have to project back into the Hermite polynomial basis state using projection there.
Okay. And for the eigenvalues problem, so is your Hamiltonian, is it bounded? Like
the dimensions of the
Hamiltonian? No, I mean the norm of the Hamiltonian.
I'm not sure if I have the answer to that. I'm sorry.
Because you run something on the IBM machine, right?
Yeah.
Yeah. For that equation itself, I'm just wondering, have you discretized it or?
Yeah. I guess there are bounds on the Hermite polynomial states that we use. So if we use 8 basis states, there's we bound it from state 0 to state 8.
So the norm of the Hamiltonian itself depends on the truncation.
Yes.
Okay.
Yes.
Thank you.
Ruben Demerjian from NRL. So I had a question for Lucas. Sorry. Really nice work. Thank you. So I'm curious if I understood everything correctly. I'm trying to kind of look for potential bottlenecks in your workflow. So if I understand it, you're doing a classical diagonalization first, and I don't really understand how that scales with the problem size. And also, at some point you have to load your data onto the hardware. Are you doing a poly decomposition or LCU, or what kind of block encoding are you doing? And have you looked at how that scales?
Yeah, so first of all, we don't diagonalize first on a classical computer. Instead, what we do is we project the Hamiltonian into our Hermite basis. And then from there, we don't do a poly decomposition of the matrix. Instead, we use the ladder operators that we construct using the poly strings. And then that we use that and multiply them to get the FP operator in terms of the poly strings from there. And then we just map that onto the quantum computer. And then while we still use classical diagonalization, the hope is that when we go to do that, the subspace is of a small enough dimension that it's fast on a classical computer.
Okay, and so the ladder operators map well. It scales well.
Yeah, I mean, it's akin to the Jordan-Wigner transformation. You've heard of it? It takes the tensor products of the poly strings in the that we have listed there.
Okay. All right, great, thank you.
Thank you, Ruben. Go to the next question.
Hello, my name is Leo, and then I just wanted to know, with regards to the fault-tolerant algorithm, I think it's still similar to like a parameterized variational algorithm. So then I wanted to know whether your results show like a better, I guess, algorithm. Does it like have less of the barren plateau problem and stuff like that? Thank you.
Yeah, so for the fault-tolerant algorithm, of course, you can still run variational quantum algorithms in a fault-tolerant quantum computer. There is no problem. And maybe your performance will get improved because you kill the error. But however, the fault-tolerant algorithm I was referring to is primarily about quantum algorithm for the linear algebra. So like there are some famous algorithms, for example, is the so-called HHL algorithm on trying to solve, roughly speaking, effectively a matrix inversion, or more professionally, quantum algorithms for linear systems equations. Basically, that is an algorithm that is not really using training method, but purely by linear algebra, and input a matrix in some form, and input an AX and a B, and then trying to get from the AX equals to B, try to get X equals to A inverse B. This kind of algorithms. So those kind of algorithms are not variational. And then for those kind of algorithms, it might be a provable guarantee that this can be better than classical counterparts. So this is what I mean by fault-tolerant algorithms.
Thank you.
So can I ask one more question to the quantum machine learning part? So you mentioned this near-term quantum algorithm. I suppose you use the quantum error mitigation to the partial FTQC simulation.
Yes, so the current calculation that I did are all classical simulation on the classical device without the noise. So then at the moment, I didn't design a quantum error mitigation problem, but in practice to perform this experiment, I think it's going to be challenging because of the practical error. So perhaps we have to consider error mitigation.
I see. So in terms of the quantum machine learning, I wonder what's the underlying principles, because, classical machine learning, we have a lot of nonlinear operators, right? Once the operators becomes nonlinear, the quantum algorithm becomes pretty restricted. You can do different kinds of linearization or like a direct mapping in terms of expanded degrees of freedom. But in terms of quantum machine learning, what's underlying trick that you could bypass this curse of the dimensionality or nonlinearity?
So that was a question about why a variational quantum algorithm has nonlinearity, because we know that quantum algorithm, quantum mechanics is linear. So why there is a nonlinearity going on? So answer is that so sometimes the nonlinearity would happen in encoding. I guess you mean the nonlinearity of training parameters.
And then usually we encode the parameters in quantum circuits by some functions like cosine or sine of the variational angle. And those functions itself are nonlinear functions. So secondly, another source of nonlinearity is from measurement. So although the main part of quantum computing is unitary, but when you are measuring it, and then so that can introduce nonlinearity. So usually those are the nonlinearity, how the nonlinearity comes from variational quantum algorithms.
Okay, I see. So your entire workflow, quantum machine learning, is basically based on the variation of quantum algorithm.
Yeah,
it's not really FTQC quantum algorithm, right?
No. So that for the later parts of the quantum algorithms, it is about photon quantum computing. And then for that part, so we use linear algebra. And primarily, we estimate the quantum advantage from encoding and input and oracles. But for the quantum algorithm, it just means quantum algorithm for linear algebra. And that would serve as a pipeline for machine learning applications like supported vector machine and some other things. So those algorithms are machine learning related algorithms. It is not exactly a neural network, but so the significant amount of structure itself is linear.
Okay, I see. Yeah, thanks.
Thank you. I'm Abhinaya from IonQ. First of all, thank you for the great talks. All the three talks were really amazing. I have a question for Professor Li and the quantum machine learning. One of the kind of the advantages that you mentioned, and also I've kind of seen in papers, is that QML can learn more effectively from like smaller data sets as compared to like classical machine learning algorithms. I'm kind of curious if you have more intuition on other kinds of advantage that QML can possibly provide over classical machine learning.
Okay, that is a good question. So it is not really about for a smaller amount of data sets. Sometimes people say that quantum machine learning might primarily work for small data sets. That's simply because quantum devices cannot really load a large data set. So that is not because it has advantage in algorithms, but it's just because if there's a large amount of classical data sets, it's going to be a significant problem in practice to load them into the real quantum devices. So what I mean for quantum advantage that can be empirical is that maybe you can observe that quantum models will need less training parameters comparing to classical counterparts for the same kind of problems. So this is observed by multiple papers, but there is no theoretical proof, but there is some numerical evidence. So one potential explanation of this from my personal view is that now, so quantum neural network itself can be regarded as a very sparse classical neural network with some spatial structure of connectivity. So, and then, so there are some like a sparse machine learning claims that saying that for a given dense neural network in classical sense, and there might be also sparse subnetwork that can reproduce similar results with comparable performance. And then maybe quantum average itself can be efficient on those kind of tasks by finding those sparse vectors, but there is no theoretical proof on those arguments. People find some evidence. I would say that it's an open problem to see how the scaling law of quantum neural network itself would look like. So potentially we can find some advantage comparing the trade-off between number of training parameters, size of the data, and also the number of qubits. So, and regarding data sets, so I think in practice, loading a large scale data set is very hard. But however, as I showed that there are some recent papers that prove in theory that at least in some complexity theory sense, quantum advantage for loading large-scale classical data sets with exponentially small scale of quantum computer is possible. So, but this requires a very large-scale photonic quantum devices. I think that is the answer maybe to your question. So, firstly, in theory, there are algorithms loading large-scale data sets that has quantum advantage, but it's challenging in practice. And in practice, maybe you can observe another type of quantum advantage, which is that you might need less number of training parameters for achieving the same amount of performance in practice. So those are my answer.
Thank you. I have one more question. So since you mentioned the Oracle sketching paper, so my understanding was that like one of the cool things about the paper was that like you get this exponential kind of speed up mainly in memory in loading the data. Is that true? Like, do you also see the exponential speed up in kind of the time to solution and time?
So there exponential speed up in time, but it is the exponential enhancement in memory.
Okay, and when you kind of tried it out practically on like the use cases that you're testing on, I don't know how easy was it to kind of like implement it and kind of see if there are any practical challenges that you faced when testing?
Primarily, it's about those classical data. The paper was proposing the so-called near version of so-called quantum oracle sketching. It has a good, but the circuits for creating quantum uploading is very complicated. It's not very implementable in the term. And a previous slide discussed the data structure is called QM, quantum random access memory. This is something I was also working on trying to make a real-world QM, but because the circuit requires almost all-to-all connectivity, so it's very challenging to prove it in experiments. But it's in principle doable, so there is no physics that tell us we cannot make it. So we expect that at some day we'll make it, but at this moment it's so hard to make those quantum memories.
Thank you. We have 5 more minutes remaining. At this time, I would like to thank Carl Thibault, who is also a co-host of this session. I have one final question to the speakers. And yeah, I'll come back to what Jason raised in the morning. And this is to all the speakers. If you have one killer app, I think is how Jason referred to it, or one quantum advantage problem that can be solved for Earth system modeling in the next 2 to 5 years, what would your recommendation be?
I mean, my personal answer is that I actually don't know. So, I mean, one of the primary reasons is to create such a killer application. So my personal feeling is that we really need better and better hardware in order to find those killer application. If there is a killer application, I think it must be closely aligned to the development of the quantum hardware that we have gradually during time. That is my answer.
Lucas?
I generally agree with that statement. I think to see an advantage in any capacity, I generally agree with that statement. I think hardware, we are currently bottlenecked by hardware, and I think I would like to see the hardware get to a point where we can actually then use fault-tolerant algorithms and find places where we can have this quantum advantage. I think it would be cool to be able to find applications in classical systems that are hard for classical computers to solve. This is, of course, difficult because we have to find mappings to the quantum systems, but I do think that this would be an interesting application once the hardware reaches the point where we can trust it, finding non-quantum problems such as climate systems that are hard for classical processors to solve. I think that would be my answer here.
Great. Thank you, Lucas. Shan Zeng, do you have a personal opinion or answer?
I think that quantum computing is kind of very important because if the quantum hardware has been developed, the software will be, I think it will be ready compared to right now, like the AI development. I think once the quantum hardware is being ready and the software is being ready as well. So the quantum computer computing for the simulation part for different kind of model is for me, I think is very important because it will accelerate the simulations, the bottleneck of simulations, because without those simulations, you can't do the training, the machine learning training and those. So the simulation part is super important, I think.
Thank you. And thanks again to all the speakers of this session.